Welcome to day 2 of the software conference. I'm Dan Calusi in the policy office, and I don't have a list of everything I'm supposed to say, but the bathrooms are at either end of this hallway. There's a room here, obviously, and then there's a room that you might have been in yesterday, hearing room 1, just a little down the hall by the water and name tags. So check the agenda and find your favorite presentations, and you can switch between rooms. Unfortunately, Robert, can you load the second presentation, Improving Grid Performance? Our first speaker is not here yet, but if he does show up, we will go next, or third, or whatever it has to be.
By the second one.
Number 15, yeah. Oh, I'm sorry. Wonbae Choi. Rob, I like your background picture there. Okay, so let's get started. So the first presentation today, again, it's not correct on this because our first speaker isn't here, but Wonbae Choi has graciously agreed to go first. Improving grid performance, innovative solutions for evaluating grid enhancing technologies, gets in generation, interconnection, and transmission planning. So please come up here, and then when you need the next slide, just say next slide.
All right. Thanks. Next, Dan. All right. Good morning, everyone. My name is Wonbae Choi from Grid Insights. Today, I'm going to present the screening tools for evaluating one of the grid enhancing technologies, which is called Advanced Power Flow Devices in the FERC order in generation interconnection and transmission planning stage. So which was developed by myself and then Felix Wang here. Okay, next page. So I think this is not the latest one, but I can go. So that, we're going to introduce our agenda here today. So before we get to the main point, I would like to introduce our experience that we actually applied GTs in the generation interconnection space 2 years ago in PJM as a renewable developer. And then we're gonna really quickly recap what's the FERC order 2023, and then 1920 is specifying for GTs, and then what's the mandatory requirements for the transmission providers. And then we're gonna share our problem statements and then proposed solutions and then next steps. Okay, next page. Yeah, so we're just newly founded consulting firm, so we have about 15 to 16 years of the industry experience in consulting and EPC and renewable development in North America. And based on our experience as a developer and a consultant, we try to help renewable developer and then utilities to solve some interesting challenges coming up. So next slide. So this is one of our actual experience during the generation interconnection process in PJM footprint. That's about 2 years ago. One of our projects in ComEd area, Illinois, having a stability issues. And then as you can see in the simplified slider diagram here, our generation is one of the generation pockets that is totaling 670 megawatts connected to the grid via 2 outlets. So obviously this is 138 kV, and then one under N-1 contingency on the right side of the grid. It is just radially connecting to the rest of the grid, and then it has really weak short circuit ratio. So it triggered a stability violation, and then the ComEd's conventional network upgrade mitigation was $180 million, building 6 or 7 miles of the new line. So that was the number 1 highlighted in the substation B. So they're trying to get 1 more outlet from the generation pocket. So then under N-1, they will still have 2 outlets, which will greatly help the grid strength. But when you develop the 105 megawatt wind project and then having $180 million network upgrade cost, that is project killer. So Felix and I, had to some brainstorming, and what's the best way to get through this situation. And then we came, yeah, then adding more grid inertia to the system or reduce the impedance of the line will greatly help that the situation. So we actually test our the concept using PSSC and then run the stability analysis. We confirmed that actually if we apply smart wires here, which is one of the advanced power flow devices, power flow control devices, it actually solved the stability violation. So we present our ideas, and then PJM eventually accepted our alternative mitigation. So we actually reduced a $180 million network upgrade down to $20 million. So using this experience, we also try to apply this idea to the ORCOD area. So ORCOD is having so much problem with stability issues. So they have so-called JTC, which you cannot hear anywhere in the PJM because PJM's grid is really strong. So using this idea that we try to solve the ORCOD's problem, and then we understand that okay, so this can actually improve the grid efficiency. So that's why we try to brainstorm one more time and then present the screening tools that the utilities ISOs can actually quickly use during the generation connection and then transmission planning stage. So next slide, please. So I'm going to really quickly recap the fourth quarter 2023 and then 1920, focusing on what's the requirements of this fourth quarter in terms of the GTs. So in fourth quarter 2023, which is for generation interconnection process, actually highlight following a list of the advanced technologies to be considered during the generation interconnection stage. So our presentation today is focusing on the third one, which is advanced power flow control devices. And then SmartWire's team was supporting all the data and then product information. And then we use PowerGem's two softwares, Tara and then the probability to verify our concepts. So one of the burden for the transmission providers is the second and then third bullet points. So now, due to the fourth quarter 2023, the transmission providers are required to include an explanation of the results of the evaluation of those alternative devices. And then the final rule mandates the process of evaluation, but not necessarily the create any presumption in favor of using them as a substitute for a traditional network upgrade. So transmission provider still needs to do the study and then try to explain why they use it or why they did not use it for these GT devices. So it should be a burden for them. So our screening tool or today's presentation is really to reply to this question to the stakeholders, and then just briefly present that actually there's a way that we can do this the screening. So next slide. And then that's why I read all the comments and the concerns in opposition side of the GTs in the fourth quarter. And then I kind of summarize in the three big criteria. So they have the issues with wide area applications. So if you think about the smart wires or any advanced power flow control devices, it's like a switching action. If you just turn it on, almost you will change the impedance of that line. That will create the bidirectional power flow. So the flow can be from A to B, could be B to A, and then some of the the generations on this side will get the benefit, but the other side will not get the benefit. But imagine if you have this like 10 or 20 in a wide area application, then it's going to be some of the applications are fighting each other. So I understand where they're coming from. And the second one is the impact on reliability and then good utility practice. So they are not really used to this smart wires concept, but actually, I think 4 to 5 years ago, New York guys actually applied this smart wires on their main backbone Central Hudson 345 kV system to increase the power transfer capability. So there are some, not many, but in North America there are some, prior experiences. And then the third one is a modeling and software limitation, because this was never considered during the generation interconnection and then transmission planning stage. So I can imagine, how hard it would be to screen all of the, violations during the generation interconnection process to verify where to put these GTs, right? So next slide. So FERC Order 1920, they have a little bit shorter list of the GT technologies, but advanced power flow control devices is one of them. And it's still transmission providers are required to explain why the above mentioned the GTs were not incorporated into the selected regional transmission the facilities. So next slide. So based on our prior experience and then what FERC order is mandating, we believe that there's no tool or guideline to assess the following problems properly. So first one is how do we determine where to put this application, especially in the wide area? And the second one is whether it can actually solve the reliability problem or not. So yeah, we're gonna answer those questions but while presenting our tools. So next slide. So this is a very simplified logic flow chart. How did we, study one of the exemplar base cases? So we start from planning base case and then perform reliability assessment, either TPL001, or it could be, the ISO's, generation interconnection study, the thermal criteria. And then we identify overloads or violations. And we go through the detailed process of, where is the potential location for this the advanced power flow control devices. And then we list up all the potential solutions. And then once more, because these GT devices can be a great tool for maximizing the operational benefits. So we run the 60 hours of the SCED analysis using PowerGen's probability. And then we calculate economic benefits such as congestion cost and then how much production cost we can reduce, and then what's the Q specific benefits. And then we compare the economic benefits between GTs and then conventional solutions. And then we summarize and compare the costs. And then we rank the GT solutions, and then we recommend the final solutions. So in the page 10 to 14, so next 4 slides, so I'm going to explain what was the examples of the outcome of the our logic, main core logics. So next slide. So first, like I say, we identify the problems and then run the contingency analysis, or it could be a generation interconnection the analysis. And then we highlight all the overloaded branches or transformers. And we also highlight all the heavily loaded branches, like, it could be tunable, but, we set it as a 90%. The reason why we also highlight the heavily loaded branches is because in case there's a one smart wire solution actually can solve 2 violations, but then it changes the power flow directions, and it can cause some other violations. So just in case, we want to make sure that the smart wires application in one area does not create any other problems. We kind of listed additional list of the heavily loaded branches, and then we also identify the critical contingencies. And then the next step is we calculate the impact of the impedance change of branch A to B. So which is probably the, you guys are familiar with the LODF, line outage distribution factor. So if you change this impedance or just completely shut down that certain lines, then which lines are going to have an impact? So we calculate all the relationship with the A and B, so IJ, and an entire, certain area. And then we calculate the range of the flow impact. So smart wires, they one of the so this LODF is also important, but also their current loading is really important, because you need to have enough headroom to adjust your impedance so that you can shift the flow. And then we verify the results. We apply the smart wires design to the system, and then we run the contingency analysis one more time, and then we verify whether there's an upgrade or the overload is solved or not. So next slide. So this is one of the like exemplar output. So we tested with IEEE from 39 cases and then 118 to 300, and then we applied it to the Oracle entire South area. We create like fictitious problem, and then we want to see whether we can actually detect a legitimate location for the smart wires location. So this is I call it as an effectiveness index matrix for contingency X. So obviously LDF or distribution factor or shift factor can change by depending on the contingency or generation location and load. Any changes in the system can slightly change that the distribution factor. So we calculate if there are 100 contingencies, we calculate all the effectiveness index for 100 contingencies. And this is one of the contingency example. So for under contingency X, on the on the first column, we highlight all the overloaded lines with their overloaded amount. And then all the first row, you can see that all the potential location for advanced power flow control devices, so which can be any lines within the same area. So for example, MISO, they divide their system into 5 different area: central, east, west, and then south. And then SPP and the PJM, they also have their own way to carve out their area. So we apply this to that specific region, and then basically in this case we apply all the lines below 345 kV system. And then we highlight all the potential locations and we calculate the effectiveness index, which is correlated to the line outage distribution factor. So for example, here line B could be a good solution for handling line 2 overloads. So for example, the 0.59862, this means if we increase 1 megawatt flow on line B, this will decrease 0.59 megawatt flow on line 2. So smart wires works both ways. So you can increase the impedance and then decrease the impedance. And then the negative sign means if you increase megawatt flow on the potential location, then it will decrease the the certain amount of the flow on the specific problematic lines. So this is how to interpret our effectiveness index. And then next slide. And then this is how we interpret the result. So for example, line A and D. So you can see that, positive number and then, negative numbers. So it could be a good solution, like potential solution for the line 1 overload, but it has a negative, the effectiveness index, which is harming the line flow on the 99 and then 100 line. So we could just easily filter out, okay, so line A and D might not be a good solution. So we'll try to, so it could be totally depending on how utility or ISOs play out. So they want to find, like, they want to really see the really clear, unique, the solutions. They can, change their, the threshold. So even for line A situation, if solving the overload line 1 could be really helpful, or the other way, by increasing the impedance, if they can solve the overload of the line in 99 and then 100, but then it will harm the line 1. But then if you can, reconductor simply the line 1, but you can solve the 2 problems, then still it could be the solution. So this is how we interpret the results. And then line B could be a good, potential candidates. We haven't actually run the verification stage, but by just looking at these metrics, we can simply filter out which can be considered as a potential solution and which cannot be the solution. So we try to minimize the matrix size so we can test the only meaningful location for the final stage. Yeah, next slide. Then we do this for all the contingencies. So this is a final feasibility metrics for all contingencies. So you will have like yes and no kind of matrices. And then we pick only the yes the solutions, and then we bring this to the final verification stage, and then we apply the how many smart wires are required to solve this problem, and then we actually run the contingency analysis once more to confirm the effectiveness of that solutions. So next slide. Yeah, like I said, once we find the potential location for the problem, the solution, we calculate the adjusted line impedance, we update the base case, and we perform the contingency analysis or generation connection studies, and then we check whether that can solve the problem or check whether they create additional problems that didn't exist in the base case. Yeah, next slide, please. Yeah, so after we verify potential solutions for GT locations, we calculate their what's the economic benefits, so the capex wise. So we have two examples here. For example, line 1, if applying alternative solutions, GT smart wires costs $10 million. But then conventional solution reconductor rebuild is a $25 million. Then obviously $10 million is has more economic benefits. So we recommend GETs. And then in some cases, when the line is really short, then this reconductor rebuild could be the better solution in terms of the capex. So we have that kind of stage. Next slide. And then we as I mentioned before, we also compare the economic benefits of the market, operational benefits. So we perform 60 hours of the SCAD analysis. So our base case will be just model all the selected GT equipment as a reliability mitigation. So we fix the settings throughout a year. We consider it as, just reliability mitigation, and then doesn't change at all. And then the second sensitivity case will be model all conventional solutions without GTs. And then compare their what's the total production cost savings and then congestion cost savings. And then the optional sensitivity case 2 could be because the smart wires or advanced power flow control devices, you can change their operating point during the real-time market and day-ahead market. So you can simply adjusting the amount of the compensation level. You can actually shift the power flow as you want it. But there will be so many different the cases and then operating scheme. So we kind of divide into the seasonal operation scheme, and based on your first base case run, you can feel that certain area, depending on their generation equipment type in that area or load the placement. So you could have, okay, in the summer, we can actually change the operating scheme of the smart wires A to a certain level. So that could be the optional study to maximize the operational benefits. And then, by using the probability by PowerGem, we can easily compare all of these, list the problems by just running one parallel simulations, and it will just summarize all the difference of production costs and then congestion cost savings and etc. So next. So I think there was 2 slides missing because I uploaded the one very final one like 2 in the morning, right? So which is typical. So I'm going to explain the missing part. So it was about the what's the key takeaways and then what's the next steps. So key takeaway is as you can see that the line outage defects is not really a new thing. Like not really trying to present very innovative things. Like this is all existing technologies or solutions we can think of. And then we just try to apply it in the wider area application using Python scripting, using all the Tara API and then probability automation scripts. So we could see that there's some potential ways to screen this application in the wide area. So we just wanted so first takeaway is that actually it's possible, and then the second takeaway is that actually it's the software or the tool limitation is not a big deal. Like what's really a big deal is the actual the guideline is missing. So because transmission providers or ISO utilities never done this before, so how they want to apply and then when and then where is going to be the really challenging. So that's the 2 key takeaways from our experience. And the next plan, we definitely want to apply this to the test cases. ISO utilities, if they are interested in applying this concept to their system, so we're willing to work with them and then apply this technology to their systems. So that is about the right time, I guess. Yeah. So I can take some questions.
We'll make sure the correct slides are on the website. Any questions? Go ahead.
Roesler or Polaris. So how much difference did you see in the benefits when you looked at the different operational cases for the smart wires where you said, okay, I want it to be static, I want it to be seasonal, and I want it to be dynamic? Did you get a range of how much did those sort of operational choices make in terms of the benefits? Because there's a lot of work that has to go on behind the scenes to obtain those.
Exactly. Yeah, that's a really good question, Ross. So basically, it really depending on the case by case, right? So, and then it depends on what kind of generation in that area, and then what kind of the load, a location nearby, right? And then what kind of the transmission line or transmission system configuration is, configured in that area. So if it's like there are a lot of wind or like, for example, a solar heavy area, then definitely you can see the congestion pattern in that area. So then you can easily identify, oh, for the smart wires is in this location, and then your congestion cost or shadow price of that area is this much high on that specific time. Then you can simply adjust the correct operating point of that smart wires for that specific ones. So it's really like try and error type of analysis. So you need to run your first base case with a fixed settings, and then see what's the congestion profile looks like in that area. And then the next stage is that you just do the fine tuning. So obviously it's going to be really challenging, but I believe that if it's a real time or day ahead, the market situation, things could be slightly more simplified because you all have already the load amount and then generation, available generation there. So then only thing you can adjust is like, impedance of the certain line. So you can do simply, brute force, like, like just all the possible scenarios and then check, oh, for this one, probably this setting is the best, and then you can apply that one on that time.
Maybe I can add something because I have some real dollar sign for you. This is not, I guess this is official, but I probably can say that we run for one of the ERCOT case. We are really targeting one specific really highly congested line. We change it, I think seasonal, and I think we see like in the range of 5 to 10 million per year congestion rate saving. It makes sense, right? Because you are really targeting a perfect use case. But what we are presenting right now is there's just so hard to apply this under the name of economic transmission planning title. There's so much hurdle. Pablo's here and definitely understand all the difficulties. That's why we are trying to start applying this under the name of reliability transmission planning, because it's easier getting stuff on the ground. I think for GET in general, there are so much people, so much talking, so many presentations, but it's really very few projects really get our hands dirty to get a feeling of what it really look like, right? We need something really running, and then we can say, okay, is there any policy, regulation, tariff need to be changed to make everything better? But we need something to get going. That's why I think that's what we are trying to start from.
Nicolas Omont from Artelis. Did you study the changing the set point of the smart wire after contingency occur? So post contingency, changing the impedance?
Oh, yes. So basically, when we run the contingency analysis or generation interconnection study, that is like you will have a monitor facility and then contingency pair, so mon-con pair, right? So you apply the contingency, and then that monitor line is overloaded. So then after we identify the location, we apply the small wires and then change the impedance of the system, and then run the power flow one more time, and then check that whether the monitor line is overloaded or not. So if it's not overloaded anymore, we can say that, oh, that specific location could be a good potential solutions for that smart wires product.
Yeah, but is the impedance different before the contingency and after the contingency, or do you change it?
Oh, so impedance changes. It's just the smart wires apply. The smart wires that works with voltage source converter. So I can provide the detailed reference later. But basically, it's a series compensation. Just it works exactly the same as a series compensation. Yeah. So you mean to apply the contingency, whether?
I mean, I understand that by changing the impedance, you can relieve the congestion after the contingency, but you have to change. Maybe it's better not to change it before the contingency, because
Okay. So this, if we apply this as a reliability solutions, and we consider that is always on that specific settings, like throughout the year. So yeah. So just like a series compensation, you just, you set certain operating point, you just leave there, like gas is, so. Okay, yeah.
So let's thank our speaker.
All right, thanks. Mhm.
And I understand that Kwok Cheung is online, so he will give the presentation that ambient adjusted ratings for improved market efficiency, design and implementation. So that's number 14, Rob. You got a lot of instruments back there. You gotta talk, I'm gonna talk guitar when next time we see each other. So you can go ahead and just, Rob, are you controlling the slides or is Kwok?
Can you hear me okay?
Okay, so Kwok, just say next slide, please, when you need to move. All right.
Okay. Is that the updated slide deck or is the old one? I sent an updated slide deck last night, but I can stick with the old one if you haven't have the new one.
I'm not sure. I'm sorry.
Okay. All right. We can go ahead and yeah, it's just there are some minor mistakes. Okay. Thank you very much, and apologize. I'm a little bit confused. Originally, I planned to be at the meeting in person. Unfortunately, I have another conference, international conference, back to back that I cannot skip. So that's the reason why I have to last minute change it to a virtual presentation. So the topic of today is ambient adjust rating for improved market efficiency, design and implementation. It's more from a application and system design perspective. I'm currently affiliated with just as an independent consultant. In the past, I've been worked with GE for the Awesome or River for the past 30 some years working on markets. I decided to semi-retire and follow the footsteps of Dick O'Neill on become more like an independent, part-time independent consultant at this moment. Now, my focus today, outline the presentation as follow. I'm going to give a bit introduction of background information about dynamic line rating, and then dig into the FERC order 881 ambient adjusted rating, and talk about the models and calculation, and then address a couple of applications related to overall dynamic line rating implementation and design, and followed by conclusion. Next slide, please. Next slide. Next. All right. So RTOs have been heavily kind of relied on the security constraint unit commitment in economic dispatch to optimally dispatch their energy resources. The keyword here is security constraint because of the fact that the system are congested, especially in the case around the world. In fact, because of the significant penetration of these renewables, these resources are not actually located at the traditional location that the transmission system is in place. So in Europe in particular, there's a lot of transmission congestion because of the change in the generation mix and the locations of the resources for generation. So congestion management become an important topic, especially as we will try to actually push for market efficiency associated with the system. So, and traditionally, that has been limited by the conductor thermal capacity defined by the static line rating, and which is kind of based on what we call the near worst case, because this is not really the absolute worst case scenario typically. And then the dynamic line rating has been potentially increased the rating to reduce the transmission congestion and enhance market efficiency. So next slide, please. So the topics of dynamic line rating actually has been around for quite some time. It's actually, if you look at some of the literature, it's actually more than 40 years in the 80s that we actually have applying some of these concepts academically. But it's in the past 2 decades that technologies, both hardware and software, has allowed the real-time and pseudo real-time measurement of transmission line rating characteristic and environment conditions, and then enable real-time and forecasting of this line rating calculation. So as I mentioned earlier, because of the economic pressures to build builds to kind of fully utilize all these power equipment capacity in both deregulated and regulated environment, dynamic rating can improve the efficiency of transmission operations by capturing a lot of these unutilized capacity and while maintaining system reliability. So there are 2 key benefits of DLR over the traditional static line rating. One is obvious, is the fact that this actually could enable significant amounts of additional transmission capacity. You can see on the kind of the blue, the green shaded area on the graph on the top right corner. Now, but in fact, you know, then there is another advantage is to actually eliminate the risk of static rating, because of the fact that, practically speaking, the worst case scenario is not really the worst case, and there is actually, in fact, remaining risk with the static line rating. Next slide, please. So illustrating an example here is basically, you can see a line was operating within the limit in accordance with the operating standard, but without dynamic line rating, this particular event must be reported as violations, and the operator would have to force to move away from the kind of the optimum point. And in the case of secure constraint economic dispatch, it will start to dispatching more expensive resources in order to so-called managing the congestion in a market fashion. Next slide, please. And the dynamic line rating approach, you know, traditionally is pretty much deterministic, and it's okay for real time. But as we actually moving into a longer term horizons of studies, probabilistic approach probably need to be taken into consideration as we see the cone of uncertainty actually grow as we look in time. Next slide, please. So I'm going to talk about FERC Order 881. Next slide. So the order released in December 2021, and is expected to be effective actually next summer 2025. And all the transmissions operators need to use the ambient-adjusted rating for the transmission line to evaluate and request for the transmission service. The TP, the transmissions operator, like the RTOs, need to establish the system and procedure to allow the transmission owner to electronically update their transmission line rating, and at least hourly, and to accommodate in some case more accurate rating such as more extensive dynamic line rating implementation beyond just the ambient adjusted one, if the transmission line choose to do so. And the TB also need to use uniquely determine emergency ratings for operational contingency and input contingent simulation of the constraint. And the TO need to share the transmission line rating and the methodology with their respective TP, and the TP need to maintain the database of each TO transmission line rating and the methodology as a password protected website. Next slide. So the major difference between the ambient adjusted rating compared to the dynamic rating ultimately is the fact that the ambient adjusted rating reflects the update to transmission ambient air temperature across the time period. In the case for dynamic line rating, the information as input go beyond just the ambient air temperature, and it could have to take into considerations of wind, solar heat intensity, transmission line, and line sec, etc., in order to really exploit the benefits of the capacity of the lines. Next slide. So I would look at the ambient adjusted rating as kind of one step towards the ultimate full implementations of the dynamic line rating. Certainly there are benefits compared to the static seasonal line rating that we have today. But over time, I think with deployment and considerations of technologies, hardware and software, we can go beyond the minimum requirements of ambient adjusted rating today. I think one of the challenges that we're seeing compared to the traditional way of doing things, because certainly if for some RTOs, dynamic line rating implementation may not be totally new, because even though it's mandatory, some of them actually implemented. And that communications between the TO and the RTOs a lot of times are through like ICCP or the SCADA. But with the order right now, the amount of data that I need to be communicated between TO and ISO, as well as archiving and auditing to be compliant to the order, the infrastructures probably need to have some changes. And now, except, now basically there are many more facilities need to take the AR into consideration compared to the old days could be just a limited set of lines. Next, please. So the order mandates the ISO to implement ambient adjusted ratings, and then that has to apply to the real-time congestion management, and the look-ahead market commitment process, as well as the look-ahead reliability studies. Also, evaluations of the curtailments of the near-term transmissions service. So there was a set of criterions related to the ambient adjusted rating, like incorporating all these ambient adjusted rating forecasts into the business process of day-ahead and real-time market clearing, and having the forecast resolution to be hourly and monthly update to the sunset and then the sunrise times, using calculation adjustments of the rating with every if it's a kind of a table lookup situation, that the temperature resolution has to be every 5 minute Fahrenheit changing in temperature, and also in conjunction with the thermal studies, like the traditional contingency analysis in the EMS, there could applications for AAR to dynamic stability analysis, RAD scheme, all that need to be consideration. Next one. Next slide, please.
Hey,
So,
Kwok,
yes.
this is Dan. I just wanted to say you have about 7 or 8 minutes left. I know you have a couple.
Okay, I'll
more
go pretty
slides.
quickly. Yes.
Okay.
All right. So next slide, dynamic line rating, focus on for the determinations methods. There are weather-based methods, temperature-based methods, as well as the site monitoring-based methods. And currently been focused on the weather-based at this moment. Next slide. And here's the conductor heat balance equations that based on that we could actually doing the maximum permissible calculations of the currents based on a steady state thermal equilibrium calculations. Next slide. Next slide, please. Yeah, so the first application related to DER is the forecasting application. And here is a use case, a weather-based approach of probabilistic DER methods. The framework basically is based on the weather predictions, try to get the mean and standard deviations of the forecasting for weather information at the selected span. And then based on the heat balance equation to calculate the capacity forecasting of the selected span and the rating of the entire line limits by the critical span at the end. Next slide, please. So there are more advanced, technology and measurement technique that actually can employ to get, for instance, the wind speed as well as the sag of the line in order to actually getting a better accuracy of the dynamic line rating. Next slide, please. Here is the another application that actually important, which is the limited exchange portal. As I mentioned earlier, traditional ways of doing it a lot of times are through the ICCP mechanism, and we need a more robust and scalable solutions to address the challenge on the exchange between the transmission owner and the RTOs or with the other external reliability coordinator. So here I actually just show some of the major data flow related to the dynamic line rating among the RTO, the external RC, as well as the transmission owner, as well as the weather vendors. Next slide, please. So the calculated look ahead ambient adjust ratings actually need to be submitted in a time rolling horizon for 240 hours. Next slide. One of the key implementations of LMP is through a project that actually through LF Energy. And LF Energy is an initiative under Linux Foundation, and Trolley basically transmission rating and operating limits information exchange is the initiative by MISO and GE Vernova to actually try to establish a more vendor neutral specifications for the APIs for the exchange. And that defined the API for the exchange of the rating and the rating related information to support the organization working to comply with FERC Order 881 and a conformance program try to provide vendors a means to demonstrate their compatibility with the defined specification and signal their commitment to maintaining compatibility. And it's also an open commons for the development of clients of API specification. Next slide. So here is a snapshot from the website of Trolley is open, and everybody can, based on the link on the right, to look into some of the open specifications of Trolley, of the implementation of dynamic rating exchange portal, the information's on the left showing the forecasting, the real-time information, real-times associated with the API associated with the forecasting submissions, as well as assessing the status of the rating, and also retrieving, recall the limits that actually have been used by the application downstream. So for those who are interested, you can actually look at the Choi website. Next slide. So application-wise, has to be, get down to the business process associated with the market systems. So that include the day-ahead market, the reliability unit commitment, look-ahead commitment and dispatch, and the real-time market application as well. Next slide. So here's just a high level of the kind of the system schematics, how dynamic line rating forecasting will fit into the constraint manager, and then feeding the downstream application of security constraint unit commitment and economic dispatch. For the day ahead, the submission typically will be in the morning, for the next day, 24 hours day ahead. Next slide. And this is the near real-time look ahead, is similarly feeding to the constraint manager for running the look ahead security constraint, economic dispatch and unit commitment. Next slide. And for the real time, it will involve the EMS, and the EMS typically the dynamic ratings through the skaters, do the calculation within the dynamic rating application of the EMS, and the calculated ampere rating as well as the weather informations will actually write back to SCADA, and then from SCADA feed to the downstream applications of state estimator and contingency analysis. One thing to note is because of the fact that sometimes for some implementation in North America, some of the RTO constraint manager is actually recycled on the EMS side, and some of the constraint beyond real time could be actually generated from the study network, and those constraints will also feed into the constraint management. And certainly the dynamic line rating need to be reflected in both the real-time and the study apps in order to get the constraint manager right information to feed into the dispatch solutions. Next slide. So here is just a exemplary of SEED formulations. You can see the typical formulations at the end. You can see the grid base case and contingency constraints at the bottom, which you can see the ALI is basically the shift factors multiply the injections, net injections, and on the right-hand side of the equations is the dynamic line rating. So we make sure that dynamic line rating limit are reflected in that constraints in order to properly run the security constraint honoring the dynamic line rating information. Next slide. So here's a numerical examples that applying to a large system, just to illustrate You can see the temperature and humidity as far as the pressure information, wind direction and wind speed on the left. And actually, if you run a correlations, you will notice that actually the wind speed is a very important data in order to impact the dynamic rating. So on the right, it actually is showing the dynamic rating flow as well as the set rating, and see the saving that actually can be achieved through the mechanisms of dynamic rating. Next slide, please. So here is showing the cost saving due to the application of dynamic rating. And so in this case, the scarcity cost comparisons and the energy and service surface cost savings are illustrated in this graph. Next slide. So basically in this presentation, we cover the basic requirements of FERC Order 81, the weather-based methods to calculate the AARs are illustrated here using a deterministic approach. And then the key applications of limit exchange portals and its applications are also discussed. We then talk about some actually incorporate some of the DLR and AAR into the business process of the overall market operations. Give an examples of the simulation indicating there are potentially tremendous savings can be achieved through a better utilizations of the transmission capacity. Two things to note is one is the more advanced measurements, equipment, and AI analytics for dynamic line rating and adjusted ambient adjusted rating forecasting could further actually maximize and realize capacity and enhance market efficiency. And finally, last but not least, the incorporating of the dynamic rating with probabilistic model in the day-ahead market would be an interesting future topics of R&D. So with that, I conclude my presentation.
Thank you, Kwok. We have time for maybe 1 or 2 questions. Anyone? All right. Well, thank you. Let's thank Kwok for his presentation.
Thank you.
And I will use this one extra minute here to let you all know. You probably heard, but FERC issued a advanced notice of proposed rulemaking on dynamic line ratings, and we are seeking comment from the industry. So please, you have 3 months, so you have some time. So please, if you're interested, file comments on that. There's lots of technical details about a potential requirement. Okay, with that, let's move to the next presentation. It's congestion and overload mitigation with optimal transmission reconfiguration experience in the MISO and SPP footprints. And our speaker is Pablo Ruiz. And you can just speak from here, and then again, next slide when you need to switch.
Good morning, everyone. I'm happy to be here. Thank you for the opportunity to present the work that we have been doing since the last year on congestion and overload mitigation in the MISO and SPP footprints. My name is Pablo Ruiz. I'm CEO and CTO of NewGrid, and also a senior consultant at the Bralo Group. What I will present is a team effort with us here in the room. Is one of the co-authors, Rodica Donaldson from EDF Renewables, and the rest of the team is participating virtually. Tom Butts from Minnesota Power, Paula Caro and Herman Lorenzon from NewGrid, Mitch Meyer from Alliant Energy, Ruchi Singh from NG, and Steve Leovy from WBI. So I will do the presentation, and the rest of the team will be available for a Q&A session. Next slide, please. The plan for this morning is to start with a very high-level overview of and background on congestion management and topology optimization. Then we will discuss a path for incremental implementation of the technology in utility and RTO processes, and we'll spend most of the time discussing 4 case studies. They are in MISO and SPP, resulting from reconfigurations initiated by external parties. So in this case, market participants, and we'll finish with some concluding remarks. Next slide. In terms of congestion management background, the traditional approach to manage congestion on power systems is to rely on a redispatch, reducing production upstream and increasing production downstream, while keeping the transmission grid itself as an uncontrollable infrastructure, so fixed or variable but not controllable. So if we make an analogy with transportation networks, this would be equivalent to increasing the tolls to discourage people from driving altogether. And of course, that has a significant cost implication. And in terms of the implications in the US, they spiked in 2022. The estimated cost nationwide were over $20 billion to manage congestion that year. In addition, there are reliability implications. Frequently, there are overloads, so post-contingency exceedances of the emergency ratings, as well as during extreme events that could be customer outages related to congestion issues. Next slide. So topology optimization is a software technology that complements this redispatch approach, reducing the need or the volume of it by finding quickly and evaluating reconfiguration options to reroute flow around the main bottlenecks. These reconfigurations are implemented using existing equipment, existing circuit breakers, or existing communications infrastructure. I will emphasize that the reconfigurations are used today and have been since the beginning of the interconnected transmission network. The main difference is that the traditional practice is to use these on an ad hoc basis, identified based on operator or engineer experience. So the idea is to provide decision support for these processes so that there's more consistent application, more transparent application, and better leveraging the opportunities that the grid itself provides. Next slide. In terms of the technology implementation, clearly one will need to first learn how to crawl before walking, and then running a marathon. So we have developed a 4-stage approach that is very incremental to leverage the promise of the technology. The first 2 stages do not require any integration with operational systems, so they're much simpler. The benefits are not as significant, but they're still quite significant, and we'll review those today in the case studies. So higher benefits are achieved when the technology is used to support the transmission and market operations. That of course requires integration with the EMS and the MMS, the market management system. So next slide. For the case studies, we will focus on the simplest implementation, which is to rely on any stakeholder. It could be market participants, could also be staff from transmission operators or system operators, to identify reconfigurations that are robust, that are reliable, perform well under a number of scenarios, and then for those to be evaluated for use by the different parties involved. And we'll go into more details in the next slide. MISO has implemented such a reconfiguration request process, and I would like to acknowledge the MISO and the MISO transmission owners' willingness to innovate in this way and to work with all of the members to provide another tool for them to mitigate congestion affecting the entire region. The process itself is described in the document. You can see the link there below in the slide. It has 5 steps. The first two steps are on the requesting party. So if there's a market participant that is concerned about an ongoing or an upcoming transmission bottleneck, they can identify that pattern, evaluate impacts, invest time in finding a reconfiguration that meets all of the criteria specified in the process. And then I would highlight that there's a number of criteria to make sure that these opportunities deliver regional benefits, do not shift congestion around, and there's no load realized unless the load serving entities in favor of it, so on and so forth. So a number of criteria. So when those are identified, the market participants submit the candidate reconfiguration opportunity to MISO. MISO evaluates from that screens first for the initial criteria, then evaluates for regional reliability impacts. The transmission operators evaluate for local implementability and any local reliability impacts. If those are passed, then there's an evaluation of market impacts and an implementation when warranted under the specified conditions. So there's again, the process itself is available on the MISO website. So next, we will next slide, please. Next, we will discuss 4 case studies. So as I was saying at the beginning, the idea is to leverage the low-hanging fruit. So the simplest opportunities. So the almost by definition, the benefits will be more limited, but it will still be quite significant, as you can see on this first case study, where for a 3-week outage of a major 345 kV line in the MISO footprint, there was a significant amount of congestion. In fact, initially it was scheduled for 8 weeks. We ahead of time worked with identifying what the implications would be for, from a congestion point of view, then develop a reconfiguration option, discussed with several of the parties involved, submitted on their behalf to MISO. MISO evaluated, the TO evaluated, approved, implemented, and this, what you see in this slide, is the ex post evaluation of what actually happened. So during those 3 weeks, so our studies indicate an almost 50% reduction in the cause of congestion in the whole area provided by the reconfiguration. So these bottleneck would have been a top 5 type of constraint in the entire MISO footprint. It became under top 10. So that was a good impact. And in the next slide, you can see part of the reason why that worked very well. This is a wind-rich region. The reconfiguration enabled a significant reduction, 86% reduction of wind curtailments under those outage conditions. So 6 gigawatt hours of curtailments took place. 43 would have taken place otherwise. So next slide. So the first case study was the impacts of a very specific reconfiguration that was rather short, 3 weeks, still major impacts, 3.5 million in savings over those 3 weeks. Case study 2 shows the aggregate impacts over an extended period of time. Since 2021 or fall of 2021, we have been working with Alliant Energy, monitoring congestion affecting their assets, and whenever there are significant bottlenecks in the region, looking for regionally beneficial options that meet the MISO, the criteria in the MISO process, submit those to MISO and quantify, expose the results. So on the right-hand side, you can see the total, the net congestion costs for Alliant Energy's Interstate Power and Light, that's Iowa utility, the net congestion over the 2.5 year period since October 2021 through April 2024. By net congestion, I mean this is already accounting for all of the congestion hedging instruments available to utilities. So these are actual costs to customers. And over the 2.5 year period, we have been able to reduce those by over 50%, as you can see. So $26.6 million in realized savings since October 2021. So major impacts for the IPL footprint. In addition, there are further opportunities which we quantify in this case at 31% of reconfigurations available not used for a number of reasons. In part, if you compare the dates, this includes opportunities since October 2021. The process itself in MISO started a year ago. So these results include impacts when there was no process and the requests were more ad hoc. So that's part of the reason. And of course, you cannot fully eliminate congestion just by this approach, but significantly reduce the implications of it. We estimate the residual congestion costs would have been just under 20%. Next slide. So the first two case studies are related to the MISO process itself. The next slide shows case study number 3, which is a little bit different. It's for a stability constraints. And stability constraints are not eligible in the MISO process to be used. Next slide, please. You can see a diagram of what this constraint is an export interface with over 1,000 megawatts of wind plants. Any major outage in the area would significantly reduce the total export from the area. There was one such outage. It lasted for 8 weeks in January and February. There was another one that lasted for maybe longer, even in the spring. We evaluate in this slide. You see the impacts in January and February. The constraint was binding 33% of all of the real-time intervals. So effectively, anytime there was some level of wind production in the area, the constraint was binding, and the associated congestion costs were quite significant to over $9 million over those 8 weeks. So now, next slide. We did study the bottleneck, even though it was did not qualify for the reconfiguration process, and identified reconfiguration opportunities to mitigate these stability concerns or stability constraints. Our ex post studies that you see on this slide for the 8 weeks of the outage indicate the savings of about 40% of the cost of congestion with the use of the reconfiguration. Again, this opportunity was not implemented in contrast to case studies 1 and 2. So those show actual results. These are potential results, but mostly provide hard data to justify implementing or spending the additional effort in studying these type of opportunities to provide further savings. Next slide. In terms of where those savings are coming from, again, this area is a wind-rich part of the MISO footprint. The wind curtailments would have been reduced by 63% with those reconfigurations. 111 gigawatt hours of avoidable curtailments that were not avoided. So very significant impacts as well. Next slide, please. So the last case study is also a little bit different. In this case, is from the SPP footprint. The first 4 case studies are mostly focused on mitigating congestion that is driven by specific transmission outages. Most of them planned, some of them forced, but the vast majority is driven by outages. In this particular slide, that's different. We're tackling persistent constraints that have been significantly binding. Of course, more frequently when there are outages, but they are binding pretty much every time, or no, under any conditions. And evaluate first some reconfigurations that perform well under every system condition analyzed, and evaluated the impacts exposed, in this case over a period of a year and a half, to 2021 through June of 2022. And the estimate for the regional savings is over $150 million over that period. We can annualize and say over 100 million per year in available savings opportunities for the region from leveraging these opportunities. I'll say that the SPP is developing a reconfiguration request process, and that process will enable these type of opportunities for being used. Next slide. As I mentioned at the beginning, these case studies are for stage 1 of the conceptual implementation process, where the requests are coming from the usually external to the RTO, but not necessarily. Of course, additional integration with the RTO processes and use of the technology in-house will drive much higher benefits. So just by taking into account what we have been able to achieve with an external request process, you can see that these additional benefits could be quite significant as well. And last slide. So to conclude, topology optimization based on our experience is quite proven. You've seen the 4 case studies. In the appendix, you can see a list of 22 case studies. In addition to these, it's readily implementable. Always a win-win-win from the point of view of economic efficiency, reliability, and resilience, and complementary to both transmission investments and other grid enhancing technologies. Dan, by the way, this is not the latest deck, so hopefully you can post that one too, so that the complementary to other grid enhancing technologies was the last addition. So in terms of next steps, both SPP and ORCAD are developing reconfiguration request processes. It would be great if other RTOs would do the same. And in terms of the implementation integration with within RTO and utility systems would drive additional benefits. And I'll stop there and happy to address any questions together with the rest of the presenters.
Thanks, Pablo. You're exactly on time. It's amazing.
Thank you.
So-
Yujie from MISO New England. I have 2 questions. First, the MISO study case is really impressive. Have you observed either TO or ISOs internalize this experience? For example, update their operating procedure when the similar outage happens, they already have measures to mitigate the congestion.
Yeah, that's a great point, Ishi. We have seen that. So it has happened that let's say for one event, we work on a given bottleneck, work with MISO and the TOs to get those implemented, and those become reused down the line. Not every event is the same. So even in the same area, depending on what's on outage, can quite significantly change not only the bottlenecks but also the mitigation opportunities. But we have seen these lessons learned being leveraged.
Second, more like a comment that I think TO probably have better network modeling on the distribution side, which ISO may not have the visibility. It caused that maybe there are some better mitigation solutions to reconfigure the network, but ISO may not have the way to detect those measures. So have you considered, or TO request you to do a kind of like a whole set of study to predict what could be done ahead of outage happens?
Yeah, that's a great point. We have worked with TOs directly to look at those impacts. And specifically in the MISO process, that's the reason for both the RTO to evaluate from a regional point of view, and then for the TO to evaluate from any local point of view. Also, we have seen on occasion TOs responding with this reconfiguration we're not willing to do, but we would be willing to do this other reconfiguration. So effectively being alerted by the impending major congestion event, evaluating what is submitted, and then counter proposing something else that would be feasible from their point of view. So it's a very productive type of engagement.
Hey, Pablo, great work. I have two questions. The first one is, can you elaborate a little bit more on how new grids, new technology application on planning, especially long-term, for example, MISO Tranche 2, that type of planning? Because if we have done great work in the planning, stuff like, still there are new resources coming in. When you plan the transmission line, you may not consider it. But if we do better work in planning, will that avoid this kind of a persistent congestion, especially in the SPP case?
Yeah, that I don't know that if you can, really avoid the persistent congestion. Perhaps you can avoid some, but there's so much uncertainty in the planning timeframes that I wouldn't venture saying that you can avoid it. But what I think the technology does offer is the ability to inform planning, to make sure that any new facilities, any substations, new lines can be leveraged and open up as many reconfiguration opportunities as possible. Many times, as part of our work, we find effectively missed opportunities. So if there were additional breakers in that substation, there could be a really powerful reconfiguration that is not available because the breaker is not there. So let's say doing transmission planning that is topology optimization aware could really open up the flexibility options. And yeah, Rodica.
Thanks. I would just add that most often in discussions with TOs, when Pablo is presenting the solution, TOs are more comfortable as a temporary solution, so it's not included in the planning models. But we do have an experience with one reconfiguration that was implemented for at least a year, and then the TO got comfortable that it can be a permanent reconfiguration, and it's included in the planning. But in all the processes that we are discussing at RTO levels, the point is that those solutions are operational, so they are not including in the planning unless TOs become comfortable that they can cover all the system conditions.
By the way, I believe Tom, Mitch, and Steve are online. So if you would like to add any thoughts on this question related to planning. We're going to the next question.
When you are discussing with TOs, what kind of limits do they put on a reconfiguration? For example, can they change the topology every day, every month? Do they need to change the protection setting when they do it? What are the limits that prevent from a large-scale deployment?
It's a great question. So keep in mind that because these are externally initiated, the review cycle can, it's not immediate. So the MISO process indicates effectively three weeks, so 15 business days. We have seen much faster implementation under, in some regions for some reconfigurations, slower for some others. Sometimes if the reconfiguration is similar or the same as one that has been used in the past, then it's faster. If it implies a substation reconfiguration, splitting the bus that may require a review by the protection team, then it could take a little bit longer. But we haven't seen, and Roderick and others correct me if I'm wrong, I haven't seen any hard limits. So I would say that both the RTO and the TOs are interested in knowing what's possible, and then they will make a decision based on the specifics of that particular event.
Yep. Somehow, my idea was that given when there is wind or where there is no wind, the flow patterns are different and the optimal topology is different. So are the TO ready to change the topology depending on the wind conditions? Or
they can be, but considering everything else that is going on the network, some of these events, as we've seen, may last for weeks. Some may last for multiple months, half a year, more. So the range, what else is on outage may also play a role in their approval. In fact, we have seen cases where reconfiguration is approved under some conditions, the same when it's not approved under some other conditions. So.
Hi, thank you so much. To get through to stage 4, is there any more work that's necessary from NewGrid side on the topology optimization, or is it just about RTO integration?
For use in stage 3, so real-time transmission operation support, no work on the NewGrid side is necessary whatsoever to support market clearing. That's another conversation. The technology is ready now. Whether the available commercial package today needs to be adapted, most likely the answer is yes, but that would depend on exactly what it means. So I would say that the seed technology is ready. The implementation is only a matter of time and priority.
Anyone else? All right, last one.
Second question is about have you ever thinking about applying this in the distribution level? There's a discussion over a DSO and considering the complexity of distribution level and the observation of potential of the DR, especially in some region in Illinois or California, it's essentially a very, very complicated system. Can you comment on that?
Yeah, I would be curious to continue the conversation offline. I think it would really depend on what the specific distribution network looks like. Sometimes in what is it, the distribution network? So depending on the footprint, distribution may be inclusive of the 50 to 100 kilowatt system, in which case it's effectively the same technology. If the lower you go in voltage, the more likely you do not operate the network as a mesh network, in which case the technologies would be applicable, but it would be a different type of implementation. Since on the transmission side, the goal is to avoid radializing as much as possible. Many times in distribution, you do exactly the opposite. So.
All right, let's thank Pablo. And thanks for the great questions. Next up, last one for the session. Grid enhancing technology benefit assessment with advanced OPF PowSyBl? How do you say that?
PowSyBl, yeah.
Yeah, Matrix. And this is Nicolas Omont from Artelis.
Thank you.
And Rob should load the slides momentarily. This is number 17. All right.
Okay. Good morning. I'm Nicolas Omont, the Vice President of Operations at Artelis, and I will present the grid enhancing technology benefits assessment with advanced OPFs, like PowSyBl Metrix. Next slide, please. So first, I would like to thank the FERC for organizing the conference and giving me the opportunity to speak today. Violet, who is in the audience, is with me today, and we can continue the discussion offline. We are here up to the end of the conference. So Just a word on Artelis. We are an independent software edition consulting company specialized in numerical optimization solutions for energy systems. So it goes from optimization servers. So some of you may know Artelis Nitro, which is a nonlinear solver used for optimal power flows, and with which we participated and won prizes on the ARPA Go challenge. We develop optimization engines like market clearing engines, mainly for European markets. And we provide consulting like prospective energy studies, long-term studies about the energy mix. The company was founded 24 years ago. We have around 8 offices across Europe and North America, and we are more than 100 experts. Next slide, please. So, I mean, everybody started with the same kind of slide. And we currently have the energy transition that is stalling. You can find the figures you want, but the interconnection queues are very large. The redispatching costs in Europe are very large. So just an example, in Germany, more than 4 billion euros in 2022 of redispatching. So figures are changing, but we are around 10% of the total system cost, and it's increasing. And we know that expanding the grid is a slow process. In Europe, as in the US, it's more than 10 years to build a new line, whereas you can build new wind farms in less than 5 years. So we know we have a big problem. So we have to make the best of existing grid to host more renewables. And we have seen a lot of FERC orders targeting this purpose. So we have mentioned this morning ambient-adjusted rating and dynamic line rating. We have mentioned topology optimization. I can add phase angle regulators or smart wires that were also mentioned this morning, which somehow, even if it's not exactly the same way to work, they modify the flows. And then the last one I want to mention is curative curtailment or post-contingency curtailment, which I think is often underlooked for various reasons. I don't know exactly why, and it's not even mentioned in FERC orders, but the benefits can be very large. So by curative curtailment, I mean very fast, not 5 minutes like in an economic dispatch, but less than 1 minute. PV panels have no inertia, so sometimes it's an issue, but to curtail them is not. It's good. You can curtail them in less than 1 second. It's okay. Wind farms, you can stop them in 20 seconds. So we could have something very fast to stop renewable generation after a line contingency. And then, battery energy storage system can also be used, even if it's not probably the best way to handle the grid congestions. Next slide, please. So once you have said that, you need to plan for the technologies, the grid enhancement technologies, and you need to plan in on the long term. And of course, no advanced technology will replace grid reinforcement. So you have to plan grid enhancing technologies together with grid reinforcement, and they can have a huge benefits to cost ratio, and they can even make some grid reinforcement useless, as we have already seen other methodology showing it this morning. So dynamic line rating or curative curtailment can indeed increase wind hosting capacity of more than 30%. Grid optimized topology, Pablo showed it, can generate an increase of capacity of more than 10%. So just to give one figure, for curative curtailment, the French TSO expects to spare 700 million of investment a year during the next 10 years. So maybe it's a bit overestimated, given that the investment of RT are around 4 billion euros a year. But I mean, this is still a very significant number that's going to allow the French TSO to integrate a large amount of wind farms and PV panels with less investments. So it's quite easy to understand why and how it works. I mean, if you do only preventive curtailment before the contingency, you cannot load the line. So in a simple system with 2 lines feeding a load with a wind farm, well, if you can, if you need to satisfy the N-1 criteria, the lines will be half loaded. Whereas if you are able to curtail the wind farm very fast after a contingency, then of course you can load fully the line. So said like that, it's simple. Of course, there is a short-term overload to manage, but you can use a short-term thermal limits of lines to manage it. Next slide, please. Yeah, so we have seen this morning that it's important to have to manage the grid enhancement technologies in operational processes. But if you do not plan for them, you will never have them in the operational process. So that's why you need to incorporate them into the long-term planning. And we have developed a methodology to assess the benefits of the technologies on a given grid or a given section, a portion of a grid. So it's rather simple in that it uses an optimal power flow, namely PowSyBl Metrix, and with which you provide various scenarios of renewable energy sources capacity with various energy sources capacity, and then you compare how much curtailment you have to perform on it if you have only preventive curtailment, or if you also allow advanced grid technologies like DLR, curative curtailment, PSTs. And then from that, you can assess either the amount of the amount of the decrease of curtailed energy, or the increase of capacity that you allow, given that you fix the amount of curtailed energy that is acceptable. Next slide, please. So this is how it looks like on a study. So in the end, you do scenarios in which you install more and more variable renewable energy sources, and at the beginning everything is okay, and then at some point you start to have curtailed energy. And if you have only preventive curtailment, this is the blue line, then it increases rather fast. And then if you have DLR in orange, or if you allow for curative curtailment in light blue, then the curtailed energy goes up slowly. And if you set a maximum acceptable curtailment level, for example, at 5%, then you can compute the additional hosting capacity of the grid. And in this case, you see that you will be able to the grid will be able to integrate maybe 10% more without without increasing the curtailment level. And this is how you can assess the potential of gates and then plan on the long term their deployment. Next slide, please. So now, after this long introduction, I will come back to how the methodology is working and how especially PowSyBl Metrix is doing this work before going back to examples about how we could evaluate transmission expansion planning projects or evaluate grid enhancing technologies. So next slide, please. So why yet another OPF? I mean, we have been speaking from yesterday and today about many security constraint unit commitment, economic dispatch, and somehow why do I propose to use another OPF to do the task to evaluate the grid hosting capacity of the benefits of a grid of the reinforcement of a grid? It is quite simple. So the security constraint unit commitment are very complex in terms of generation dispatch complexity. And each year, and when I come to the conference, I see new complexity being introduced. So this year it was synchronous condensers or ramping constraints. So every year something new. And so this is the first axis of complexity that is present, and that well, it takes a lot of time then to compute the results. But this is only one of them. The other one is the grid modeling complexity. And well, we know that the ARPA-E challenge, for example, focused on having AC OPFs and not DC ones, so that you can manage voltage issues and manage reactive power. And so it increases the modeling complexity. When you do that, well, the unit commitment has to be simplified. And this is the case on the ARPA-E Go challenge. The unit commitment is not as complex. And even if you go to a grid like the grid of Quebec, with voltage stability issues instead of thermal limits, then the complexity of grid modeling is even more complex. But that's not all. And when you do grid reinforcement study, you need to model accurately grid operation, because that's the first and most important thing to model to get accurate results. So instead of having a fixed grid, you need to model preventive and curative grid actions, like topological switching, like curative curtailment. All these actions that are very important to model if you want to assess the benefits of a grid reinforcement. And that's why PowSyBl Metrix was designed to do grid reinforcement studies and focuses on this last axis. So as we know that we will focus on integration of variable or renewable energy sources, we know that we need to do hourly simulation with a lot of annual scenarios. So we really need something that's very fast, because we are going to need to assess a single reinforcement. We are going to need maybe 100 simulation of 100 of hourly annual simulations. So we cannot wait. We cannot have. We cannot wait for 10 hours for each of these annual simulations. Then it's long term. And somehow we need to address first the main problem, which is energy transfer. And voltage management will follow. Anyway, the scenarios are very uncertain, and trying to manage voltage issue 10, 15, 20 years ahead, it's not possible. So DC approximation is enough. And then the last point is that we should not focus so much on unit commitment. So we can take an external unit commitment computed on the base case, and then only have a marginal, using a marginal cost model to assess the marginal impact of the new asset. It's usually enough to do a benefit analysis. So that's why PowSyBl Metrix is focusing all the complexity on the grid operation in order to have the best trade-off to make the best reinforcement studies. Next slide, please. So PowSyBl Metrix is part of PowSyBl, which means Power System Blocks. So it's a framework written. It's a framework dedicated to electrical grid modeling and simulation. So I'm sorry, it's not the last version of the slides. So it's governed by the Linux Foundation Energy. Alexandre Parizeau is here to represent the LFE. The steering committee of PowSyBl is composed of the French TSO RTE, Artelis, and some other companies. So it's open source with a commercial friendly license. Namely the weakly contaminating MPL v2. It has a large community of users, and it's operationally used by European grid operators, meaning they are using it in daily operational processes. It can perform grid computations, power flows, OPF, security analysis. It can handle various grid formats. And so in North America, I suppose SIM, PSSC, and MedPower are the ones that are more interesting to hear. It's rather user-friendly with a Python interface, network and substation visualization libraries. It can perform various kinds of grid modeling. And what is important is it's enterprise grade. So it's Java-based with C or C++ libraries when numerical performance is needed. but Java is better for integration in enterprise systems. It has the open source security foundation silver badge for managing security of the cyber security of the tool. Data format version management and a high standard for the CI/CD with a high level of code coverage. Next slide, please. So, and PowSyBl Metrix is indeed, as I told you, a security constraint DC optimal power flow and not a simple power flow. And despite that, PowSyBl Metrix for one time step is 20 to 100 times faster than an AC power flow. It's a DC model. So here I somehow compare things that do not completely compare to with each other. But indeed, it's really very, very fast. It's written in C++, and it comes with its own mixed integer programming solver. So meaning that you can use it out of the box. And the fact that it has its own solver also explains its performances because it's really tuned to the needs. You can model grid operation, as I told you, so HVDC set points, phase shifting transformer or phase angle regulation transformers, they're the same thing. Line switching, you can configure redispatching based on the generation marginal costs, permanent limits, temporary limits of lines and of transformers. It's tuned to model a large number of variants, so typically hourly variants for annual scenarios, so 8,760 points, in which you can use time series to model demand, generation, line limits, redispatching cost, or all the parameters. And it allows flexible definition of contingencies and remedial actions, whether the remedial actions are curative only, preventive only, also curative, but for specific contingencies. Next slide, please. It has 3 computation modes. So the most simple one is a DC security analysis. So it's basically a DC power flow, no optimization, it just gives you the violation. Then the second mode is a SC DCOPF without redispatching. So using only 3 remedial actions that are the topological actions, either preventive or curative, PSTs, switching, HVDC set points. So in this case, there are no costs involved, and the objective is to minimize the maximum flow violation. And the last mode, which is the one that looks like a security constraint economic dispatch, a very simple one, without look ahead, without anything, is minimizing the redispatching cost while satisfying the flow constraints, but still taking into account topological remedial actions, preventive, corrective, everything I already mentioned. Next slide, please. So now, 2 examples on how to use it in long-term planning. Next slide, please. So first, the grid reinforcement benefit analysis. So same thing, this is not the last version of the slide. So we applied it on the RTS GMLC example, but the text is about the general way to do to study grid reinforcement. So in case of studying grid reinforcement, you've got the base case with no reinforcement and only preventive curtailment. Then you've got a second case where you add, for example, an additional line. And the last case is where you have a grid enhancement technology, either with or without the additional line. So it gives you, if you count, 4 different scenarios. For each of them, you can compute the flows and the congestions, and you can compute the redispatching and curtailment costs. And you will see that they decrease with grid reinforcement or get deployment. So, and then for each of the scenario, well, the assessment is quite simple. you load the network, then you map the non-dispatchable generation on the load, and also the initial set points of the dispatchable generation. So these set points usually comes from a more complex security constraint unit commitment that you have performed. And then you run it and with a full N-K analysis. So for example, on the RTS GMLC, it was single contingencies on all the elements of the grid. Next slide, please. So in this very simple case, we added a 500 megawatt line between zone 1 and zone 3. And then we ran the tool over the year and computed the savings in terms of redispatching costs. So let's say that we found $3.7 million dollars a year. Let's say that the line the line annuity would have been 3 million, then the investment will be accepted. And you can dig a little bit into it and look at the weekly savings. And in this case, you see that they were constant. That is, that where the savings were the same in winter or in summer, which is not always the case, but to show that you could have more insights into the results. Next slide, please. And so as I told you, it's very fast. So in this case, the test case is not huge. I mean, the RTS GMLC is only 120 branches, but the computation time with all contingencies and 1 year of hourly time steps, so 8,760 time steps, was done on a basic laptop on 1 core in 55 seconds. So it's 0.01 second per time step. Which, I mean, allows you to study really a large amount of variance, which is needed. We have seen that, for example, in Pablo's presentation, you need to study maintenance, planned maintenances, and everything that can have a big impact on the benefit of a new line. You have to think about the maintainability of the grid and to all the cases that could happen. And we cannot continue to assess the benefits only on the base case with all the lines that are here. Next slide, please. And lastly, I would like to come back to the figure that I showed you at the beginning on the hosting capacity. So next slide, please. So I showed you this figure where you see the sensitivity of the curtailment in terms of percentage of energy with respect to the installed capacity of renewable energy sources. So in this case, there was DLR in orange and curative curtailment in blue. And so what you see is that DLR allows to delay the curtailment. But at some points, the blue line and the orange line are parallel, meaning that you have saturated the DLR. They do not provide additional curtailment reduction. Whereas curative curtailment at the beginning is like DLR, but then it continues to increase. The curtailment reduction continues to increase when you increase the variable renewable energy sources installed capacity. Meaning that in this specific case, and it may change in other situations, at the beginning, it could be good to start with DLR, but at some point, switching to curative curtailment will be the only way to continue to increase the reduction of curtailment and to allow allow the system to integrate more renewable energy sources. So yeah, that's the kind of conclusion we can have, well, would be happy to study other systems. Next slide, please. So to sum up very quickly, I mean, the message is quite simple. we need GETS to do the energy transition, and we need to streamline cost-benefit analysis of GETS. I mean, FERC order on 1920 is all about it. If we want GETS to be deployed, and not only the GETS that we think we are going to deploy tomorrow, but also those we think we are going to deploy in 10 years, 15 years, where we will be operating the system differently. Especially, curative curtailment may look like science fiction today, but maybe not in 10 or 15 years, and we have to plan it as of today. We have to anticipate in planning studies. We have also to anticipate by asking wind farm developers the SCADA connections, the SCADA links that will allow to do curtailment in less than 20 seconds, or that kind of thing. So all this must be planned as of today, and PowSyBl Metrix can power the analysis that can help to make the right decision on the path to deploy the GETS, and then on their impacts on each of the grid reinforcement that are going to be planned in the next 10 to 20 years. And of course, as it's open source, well, you can try it by yourself. And I'm happy to discuss it after in follow-up discussions.
Thank you very much. We have about 2 minutes for questions before we break for lunch. Go ahead.
Russ Filbert, Polaris. So the post-contingency response approaches, I think you're right that they're really underutilized and could make a big impact, particularly in the example that you gave with curtailment, corrective curtailment for renewables. Most of the GETS technologies can be easily implemented as post-contingency corrective actions, but there's some that are a bit more challenging. So specifically, I wanted to ask you about, opening lines as a post-contingency response is easy. Closing lines as a post-contingency response, that's a bit trickier to deal with in terms of a modeling and implementation. Have you addressed that, and what have you found as an approach? Because you need to do it fast, and you're not going to solve an optimization to get the line flow on your closed line.
So we can discuss that, but RTE has currently started to do wide-scale deployment of an OPF that is run every 10 seconds, and that can do what you said. So that is, it's a local OPF on 100 nodes each time. That is a DC OPF, no security constraint, and that is able to take decisions within 10 seconds with a look ahead of a few minutes. And this OPF is indeed able to decide whether it's time to open or reclose a line. It doesn't make much difference from this point of view.
We'll talk about it separately. Okay, thanks.
All right. Probably can squeeze one more in if anyone has a question. Anything online? All right, well, let's thank our speaker. And we will break for lunch, and then I think the sessions pick up at 12:30. And please keep your badge if you leave the building. And anything else I should say? All right. Thank you, everyone.
All right, y'all, if folks could start having a seat, we're gonna go ahead and get started. Welcome to session WA2. So for folks online, we're here in the commission meeting room, and this is the DER panel. I'm biased, but I'm really excited for this one. And so first up, we have Brent Eldridge from the Pacific Northwest National Laboratory, and his presentation is titled Simulation Platform with Integrating Security Constrained Unit Commitment, DER Aggregation, and Distribution System Models. So thank you, Brent.
Okay. Just wait for the presentation to come up. Okay, thank you. I apologize for the title. It's a bit of a mouthful, but thank you for letting me present our work today. And I guess first I want to say thanks to all the FERC staff for putting on this conference. Every year it brings together a really good group of ISOs and academics and industry and national labs to talk about, what are the hot topics in power systems development. So appreciate that. And we can go to the next slide. Oh, sorry. Yeah, so what I'll be discussing today is kind of a 3-year project that was funded through DOE Advanced Grid Modeling Program. We're a little bit over halfway past that, or halfway through the project. And I also want to thank our collaborators at Stevens Institute of Technology in New York, the MISO advisors, and Gurobi for providing the solvers for the project. Next slide. Okay, so for the talk, I'll kind of go through 3 sort of sections, a little bit in the motivation on FERC 2222, and then we have a pretty sophisticated simulation platform that has DER aggregation, SCUC and SCED model, and distribution feeder kind of modules to it. And then I'll talk a little bit about test cases. We're kind of in the middle of the finishing up the platform development. So the test cases section is a little bit more, this is what we plan to do, than what we've, than, final results. And I guess also good to note, the results that I will present are all basically preliminary. Next slide. Okay, so these next couple of slides kind of go over FERC Order 2222 as background and motivation for the project. So Order 2222 requires ISOs to implement participation models for DER aggregators. Amongst those requirements, so one major one is the participation capacity threshold is lowered to 100 kilowatts. So if you have 100 kilowatts of aggregated resources, you can participate in the wholesale market. Another requirement is trying to get as broad as technically feasible geographic aggregation. So this could potentially mean having aggregated resources that are located at different nodes in the transmission system. And that could potentially lead into reliability concerns or unscheduled power flows. And the third major part is so small size of resource, geographic aggregation, and that the DERs are located on the distribution grid. So this introduces a modeling gap, essentially, where the ISO's SCUC and SCED models don't necessarily model or don't model what's happening on the distribution grid, and that could create some operational uncertainty if there are changes in distribution system conditions or possibly distribution side constraints that prevent the DERs from being dispatched. Next slide. So yeah, this slide kind of goes over a lot of those things. We're focusing, Order 2222 also has a lot of other requirements to it. We are mostly focused, being at the software conference, we're focused on what types of software upgrades might be necessary to comply with FERC 2222, and kind of trying to quantify what are the operational risks of how DER aggregations would participate in markets. Next slide. So the different ISOs have all submitted implementation plans. I won't get into any of the details to those. The one thing to bring your attention to on this slide is just that there's different approaches that different ISOs have adopted to comply with 2222. And one of the major ones is geographic aggregation across multiple nodes. So a lot of these implementation plans are not final. those are just what is kind of in the regulatory pipeline right now. So CAISO and ISO New England have proposed zonal aggregation of DERs, whereas the others have all initially proposed nodal aggregation. So DERs aggregated at a single transmission node. That has had some pushback, and so that's, I guess, still up in the air of what they will decide in the end. Next slide. Okay, so the next few slides, this slide, I'll kind of discuss the broad overview of the simulation platform that we've developed. Kind of, as I said at the beginning, the goal of this exercise is really to create a simulation platform for wholesale market operations. So this is kind of in the day-ahead and real-time market timeframe. Simulate how would an aggregator aggregate multiple small resources, submit that as a single resource into the ISO SCUC model. ISO solves SCUC or SCED, and then sends the pricing and scheduling information back to the aggregator, disaggregates that schedule into the single DERs, and then we model that on the distribution feeder to measure what is the actual output of the aggregation. And then there's kind of a final loop at the end, assuming that there's imbalance. We're measuring what is the expected transmission power flow deviation because of that operational uncertainty. So to put all that platform together, we have a few different models. So the day-ahead and real-time market is modeled in Prescient. Prescient, of course, uses egret to solve the SCUC and SCED. We chose that specifically because egret has highly, state-of-the-art contingency constraint solver. Then the DER aggregation and disaggregation modeling we developed in Pyomo. Feeder modeling is implemented in GridLab D, and then the post-DER dispatch DC power flow is implemented in egret. Next slide. Okay, so for the aggregator model, we presented kind of our approach to the DER aggregator model last year, and we've implemented a number of improvements to share this year. Most of those have to do with either moving the simulation from just a day-ahead simulation to day-ahead and real-time. So we've developed methods to put the solar, to take the day-ahead solar forecast and put that into 5-minute increments in the day-ahead market with typical noise. So we aggregate solar that way. Battery resources are aggregated kind of using standard state of charge modeling or state of charge management formulation. So this introduces some constraints that are invisible to the ISO. So we've improved the way that the storage model generates opportunity costs that go into the aggregator's offer. And then there's demand response is the last resource type that we're using. Last year we presented kind of the approach for DERs. Kind of the big challenge with it was we wanted to have a model where demand response is presumably one of the major components of DER aggregator resources. And currently they're not a huge part of the market. So we developed an economic utility function approach to estimating how they might offer. And so that has a lot of details to it that you could look up from last year's presentation. And so that's basically how the DIRA is set up. We can configure this different ways to have different capacities of the different resource types. And then it aggregates those resources, which might be very, very small, and puts them into resource blocks that are at least 0.1 megawatt, so 100 kilowatts according to the market rules, and only up to 10 offer blocks. Next slide. Yeah, and so this slide, we had some computational issues getting large enough scenarios to run last year. And so we spent a lot of time improving the speed and robustness of the offer algorithm. So here in those two columns on the left, we have the profit optimization algorithm, which presented with last year. This is kind of a extensive figure out how much power the aggregation can provide at each time period throughout the day ahead market, and make all of those optimization solves to compute cost curves for each time period. We've replaced that with this direct cost algorithm that, so especially for storage, looks at the prices over the time horizon to calculate opportunity costs, and then simplifies so it makes it simplifies this down from solving 24 times 10 potentially optimizations to just solving one at the beginning and then computing offer opportunity costs from that. So in the table, we can see the simulation time is for the overall simulation. Once we change this offer algorithm setting, we can dramatically reduce the time of the overall simulation. Next slide. Okay. Yeah, so the other thing we also presented on this last year, the aggregator model has different modes of operation. So the main two are either schedule following or profit following. So on the left, we have schedule following. It has some deviations from the SCUC dispatch. So SCUC dispatch is shown in blue, and the actual DIRA dispatch is shown in green. Those deviations come from a number of complicating factors within the individual DERs that make up the aggregation. So the demand response has a boomerang effect to where if it is dispatched in one period, it may need to recuperate that energy in a neighboring period. And similarly with battery storage, it has to maintain its state of charge throughout the time horizon. So that's why there's some deviations on the schedule following mode. On profit following, we obviously get much more deviations. And so in this case, the DIRA, after following prices, it shifts its dispatch more into the peak periods of the day. So there's some questions about why was the DIRA dispatched this way to begin with, and we're kind of looking into that. So there's multiple reasons why this could have occurred, and so one of those being this is a large SCUC model that's being solved to an optimality tolerance. The DIRAs are small and insignificant compared to this optimality tolerance, so it could just be a bad solve, or it could be within the offer generation algorithm itself is not necessarily optimal, and of course it doesn't consider the full interior interior constraints of the aggregation. Next slide. Okay, so the next thing that we did is implement multi-node resources in eGrid and Prescient. And so essentially what we did is take the thermal generator model that's included in Prescient right now and added a distribution factor formulation for that and a new specification so that you could specify a resource that is located at multiple nodes. And so the way that this distribution factor works, right, is if your total generator output is 1 megawatt, you might specify a distribution factor of 50% at node A, 50% at node B, and the SCUC model will assume that you have half of a megawatt at node A and half a megawatt at node B. So it's a fairly straightforward implementation. We tested this in the RTS GMLC system. So it's kind of a smaller, moderately sized system. And part of the, so I guess two things I want to say on this slide is, so first there's how we generate the DRAs. We are looking at the distribution feeder at each node and placing DERs at individual distribution nodes. The distribution nodes that are available will change. So the overall capacity of your, reset. So what we want to say with the bus selection procedure affects the footprint is we configure to have like a pool, in this case of 50 DRAs, or sorry, this is 10 DRAs. And those 10 DRAs, if they're located at different nodes, the way that we aggregate might entail those nodes being, those DERs being located at different transmission nodes than if we specified that all of the aggregators were single node aggregators. So when we do this, this means that some DERs may be responding to LMPs that they aren't responding in the single node case. And so we have the two plots on the right. In the orange, this shows the hourly deviation by different tolerance levels. So the way we defined acceptable multi-node aggregations is we solved a base case scenario to figure out which lines were most commonly loaded or most highly loaded with the least headroom. Take the PTDS from those lines and define different tolerance levels. So each line in these two plots comes from a different tolerance level on the PTDFs. And we take the infinity norm, so take the max distance, the max difference between PTDFs. If they're below a certain threshold between two nodes, then you can aggregate them. Okay, so that means two nodes can be aggregated as long as the PTDFs are basically the same, and setting different tolerance levels for that. When we do this, so the hourly deviation in orange doesn't, in this case, seem to be affected very much by the PTDF tolerance level. The major caveat to that is that this is just looking at a single day. I don't believe that this day has any transmission congestion, so it's kind of an expected result, and we need to simulate a longer horizon to see more scenarios where we could see actual differences. And then the blue on the bottom, instead of deviation range, you're looking at instead of deviation, you're looking at the range of deviations amongst these 10 different DRAs. So in the middle of the day, some DRAs are operating fairly close, some are operating fairly far away, and that creates more operational uncertainty. Next slide. So I think I'm a little bit short on time. The last pieces here go over how we're modeling different feeders. So this slide, it's essentially describing one of the assumptions that we're using on the feeder is we have pre-existing feeder models that serve a nominal megawatt amount, and that megawatt amount is different than the load on the SCUC node. So there's a scaling factor. The assumption is that this represents multiple feeders that are parallel at that node. Next slide. And this is just kind of going over how the DERs were placed. So we can skip that. Next slide. And this is the co-simulation setup. So we have one federate that's modeling prescient SCUC and SCAD, and then each DERA is modeled within that same Python process. So that's all in one federate, and then each feeder has its own federate, and then there's a second federate for each feeder, which is the utility, which looks at possible constraint violations and takes corrective action. Next slide. And this just goes over what that corrective action looks like, doing a very simple kind of scaling of the existing DER dispatch until the violation is resolved. Next slide. And we have some questions about what are the reasonable assumptions about this process? Like, what's a reasonable action for utility to take? How much visibility does the aggregator have to the distribution system? It's basically that. Next slide. And we're planning to scale this up to the FERC PJM test system. This was published, I think, in 2012. So it's a larger scale system than the RTS GMLC. Next slide. And yeah, so that's it for the presentation. I know I'm a little bit over time, so thank you for bearing with me.
Thank you so much. We are now going to open up for questions in the room and online. For folks joining us online, please put any questions in the Q&A. And are there any questions in the room to get started?
Thank you. Kazro Musley, Hitachi Energy. You mentioned the ISOs each have adopted either zonal or nodal model. Did you do your study based on nodal model? That's one question. The other one is basically the tolerance being 100 kilowatt and versus the tolerance in the optimization. Did you do any study to see how does that work out, how reliable the solution is once you do? Because one of your examples was showing that you could not quite justify the end results. Did you do more studies to figure out whether consistently you get bad results, or is this something that just happened in that test case?
Is that the first dispatch case? There is the schedule following in
general, just the tolerance being in the optimization versus the actual 100 kilowatt cutoff.
Yeah. So for your first question, we haven't used an actual zonal model from one of the ISOs. So I know CAISO has these sublap zones. There's some work involved with re-engineering what those zones are and putting that into a model. So the PTDF tolerance approach that we used was kind of in place of knowing what the actual zones could be. We could also kind of develop our own zones doing like a k-means clustering type algorithm. But for the general purposes, I think the PTDF tolerance approach is fine. And then your second question was if the anomalous dispatch was anomalous or kind of expected. In the so if the DERAs are following their profit incentives, I don't think that it's all that anomalous. So yeah, so there's the issue with constraints that are behind the aggregator that aren't showing up at the ISO level. And I think we do need to do a better job of figuring out exactly, is this solely due to the constraints, or is it due to like an optimality tolerance? The other issue here is when we have the multi-node aggregations, which was not part of that slide, but when you have one aggregator that's potentially responding to two or multiple LMPs, there's really no theoretical guarantee that they would be able to, or that their economic response would match what the ISO's dispatch is. But yeah.
And I have two questions. The first one, you were talking about the direct cost algorithm. Can you talk a little bit more about the block cost by resource and just what assumptions are used for those resources?
Sure. Yeah, so we have solar, demand response, battery. Solar bids in at one block at $0 for whatever capacity is available that for that period of the day. Demand response, I believe in the direct cost approach, we're now doing, so I guess first pass demand response would be a single block. We look at what level the demand response is dispatched at and compute the cost to dispatch it there. There's a nonlinear Cobb-Douglas function for estimating that cost. And then for storage, we look at the prices throughout the day and figure out what the opportunity cost is for dispatching at that period. So I believe, so each resource on the first pass produces one block of whatever quantity that resource is providing. And then on a kind of a second pass, we aggregate those costs so that all of our blocks are at least 0.1 megawatt. And so there could be some averaging of different resources doing that.
Thank you. And then second question is, I know we kind of ran out of time at the end, but do you mind speaking a little bit about kind of next steps and challenges that y'all are trying to address?
Yeah, so the next steps, we're really, so the simulation platform is set up, and now we're doing the work of figuring out which scenarios we need to run to look at, one of those metrics is how much power flow deviation gets caused in different cases. Power flow deviation, the nodal deviations, yeah, and figuring out, what makes sense for our multinodal cases, what makes sense for our single node cases. We're on the verge of being able to solve the FERC test system. Yeah.
Thank you. Any questions online? Any questions in the room for Brent? All right, well, with that, thank you so much. Next up, we have Daniel Roesler from Utility API and LF Energy, and his presentation is titled Standardizing and Automating DER Company Registration and Connectivity Establishment for Utilities and Other Centralized Systems.
Howdy, everybody. I'm Daniel. I'm the Chief Technology Officer and founder at Utility API. And I am also the maintainer of the connectivity working group and the customer data working group at the Linux Foundation Energy, or LF Energy. specifically the Carbon Data Specification Consortium. We can go to the next slide. Just a little bit about me and the working group. So I've been at Utility API for over a decade. I'm also the working group maintainer. I'm also the former vice chair on the board of the Green Button Alliance, which is a standard for customer data access in both the US and Canada. I've contributed to many regulatory technical working groups around data access for utility data. Utility API is used by thousands of DER vendors across the US and Canada to automate data access. We can go to the next slide. So for the first half of this presentation, I'm gonna go through a little bit of the organizational structure and the reason why these specifications exist. And in the second half of the presentation, I'm gonna talk about how that is applicable and why this matters to real-time markets and DER integration into the wider grid. So just to kind of start off, we can go to the next slide. I'm going to go through them pretty quickly because they kind of jump through. So the Linux Foundation is an open software foundation. It's a nonprofit. Within the Linux Foundation, next is the organization called LF Energy, lfenergy.org. That specializes in utilities and grid system open source software. And within that, next slide, there is a standards and specifications organization that focuses on open standards. So not open software, but open standards and protocols that can be used by grid systems. Next slide. And within that, there is a consortium called the Carbon Data Specification Consortium that specifically focuses where it started was it was focusing on carbon accounting and carbon measurement. And within that consortium, there are 3 working groups. Next slide. The connectivity working group, the power systems data working group, and the customer data working group. And so I'm the maintainer of working group 1 and working group 3. And then we have another working group that focuses on power systems data. So these are the kind of logical splits between the specifications. So these working groups write open specifications. That's what their goal is. And so with the connectivity working group, we are writing connectivity specifications. And with the customer data working group, we are writing specifications on how to securely access confidential customer information like smart meter data, like bill data at utilities and other systems. Power systems data, similarly, is how to access and the schemas and open formats for accessing power systems data. So we can go to the next slide. So the problem next is a lot of companies out there where this got started are asking, what are my carbon emissions and what can I do about them? And then in addition to that, next, governments are asking, how can I speed up the deployment of clean energy technology? So these are the 2 kind of questions that we're all grappling with in this specific consortium. Can we go to the next slide? So the calculation for these is next. You have an emissions factor is basically your one of your variables, and that's obviously way more complex than that. And then next, you have energy usage, and next you multiply them together and you get your carbon impact. And so that's the basic calculation that this consortium kind of started in, and that's what the Googles and Microsofts of the world, when they talk about their emissions-free goals, this is the basic calculation that they're doing. And so the problem with that is next, the emissions factors are hard to understand as we are talking about renewables and markets and DERs. It's very, very hard to understand what the emissions factor are, especially if you're trying to do it for a specific location like a data center, for example. And then next, the energy usage is actually really hard to get because it's siloed in many, many different entities like utilities or ISOs or like in ERCOT in Texas, for example, with Smart Meter Texas. In Europe, it's a whole different ballgame as well. And so next, the first part, that's kind of the dividing factor between the 2 working groups. The emissions factors are the power systems data working group combined with the connectivity. So you need to bootstrap access to that data because in general, it's not public data. You have to get allowed to see it because it can be considered confidential information. So you have to have that connectivity, plus you have to have the actual schemas of the formats to do it or to access it. And the next, the energy usage is the connectivity plus the customer data work. And so those are how we kind of split and organized the working groups at the CDSC. Okay, can we go to the next slide? And the next. Okay. So the major thing that we're focusing on here, and why I'm participating in this and trying to make this an open standard, is that calculating carbon impact once is easy, and calculating carbon impact at scale is very, very hard. Because to calculate it once, you can just walk over to the filing cabinet and pull out the bills and type them into a spreadsheet and like look up the things on the website and hand type them in. So that is totally doable. But in order to automate that, you have to automate every single step of that value chain. You have to automate the data access. You have to automate the power systems data working, or the power systems data lookup. You have to automate the approval and sign up, because there are thousands of DER companies out there, and there are new ones getting created all the time, right? You hear about a new car company. You hear about a new like heat pump company. You hear about a new demand response company, and then the old ones, they either get bought or merge, and it's a very, very constantly shifting market. And so you have to automate all of that in order to make these functionalities possible at scale. So can we go to the next slide? Why is scaling so hard? And can we just skip through like to the end of the bullets? Because I feel like with me not clicking, I just click it through. Yeah, go ahead. All right, perfect. Thank you. Oh, so there are a whole bunch of things that we have identified about why is this hard and why have we struggled to adopt DERs and program participants and things like demand response or energy efficiency programs in the past. And there's a whole bunch of stuff here, but some large takeaways are the industry is incredibly fragmented. Everybody has their own proprietary way of doing things. It's a very manual process frequently. Data formats are kind of ad hoc because they're built up by individual utility programs or regional programs. And often the onboarding process is cost prohibitive. If you have a new awesome smart charging app for EVs, you're probably only a 20-person company and you're looking for investment, but you're not going to get that investment until you go through 6 months or a year worth of onboarding into a market. And so there's a huge barrier to entry for DERs to start to participate in a lot of programs. And so that's one of the major reasons why we're making this open standard, to try to remove that barrier and allow for more easy access to sign up and get connected to things. We go to the next slide. So what are the components of a scalable connectivity and data access standards? So this is for the connectivity working group. We can go to the next slide. Next. So the first one is discovery. Since the market is so fragmented, you have to figure out who is offering what. You have to figure out what utility is offering what program and what sort of capabilities and what sort of functionality. Some utilities are going to be deploying things at different rates. You're going to have, for example, PG&E has a Share My Data program, and Ontario, Canada has a program for data access for all of their utilities. But, you know, Austin Energy, where I am, doesn't. And so you don't know any of these things unless you actually look at them. Well, that's something that you can automate. And so discovery is a big part of scaling up a system. Next. The next one is registration and connectivity. Currently, in a lot of these places, you have to submit an email or submit a form. And then there's an email exchange over 6 months of back and forth to get stuff. And then you get an encrypted email with your token, and who knows how that goes. And so I hope that there's people in the audience and online who have tried to go through these things before, or tried to, on the other side, tried to onboard DER vendors. And it seems like it's a very improvised thing. And so that's one of the things that we're aiming to solve here, is that for people who need to onboard external companies into their systems in order to gain some sort of secure access to APIs or protocols or some sort of program, we are trying to create an open standard that solves your problem of that. So you can worry about your actual protocol and your actual running of your system. And this is just kind of a drop-in system that you can do. Next. So for customer data, that's private information. You need to get explicit customer consent. And so authorization is a major part of that for that working group. And the next, the actual data access, the formats of the data, that sort of thing. And then we can go, I think, 3 slides ahead. Okay, so the first two, the discovery and the registration and connectivity establishment, are the focus of the connectivity working group. And those are split into two specifications, WG101 and WG102. And those are the server metadata. And so that's how a server or a utility or other central entity, an ISO, can publish a endpoint that says, hey, this is what I offer in a standardized format. And then the client registration is a protocol where you can, as a client or third-party DER or whoever it is that is wanting to use that functionality, you can use that protocol in order to register with that entity, and all of the messaging, all of the management is built into that. And then next, this is the last one is the actual individual protocols that you're trying to do. In this case, power systems data and customer data. We can go to the next one. So the actual specifications for the connectivity working group. Keep going. We can go ahead, I think 3 slides or 3. Yes. Oh, one back. Yeah. So there are 2 specifications that I described previously, how utilities and other centralized entities can disclose what data and capabilities they offer. And so that's a standardized format that DER vendors, aggregators, platforms can use to basically scan the internet or scan utilities and see if they're starting to offer capabilities. And if they are, that would automatically get detected. So it's similar to like a search engine crawling the internet. You would be able to crawl these endpoints and see what capabilities they offer. So that's the connectivity or the discovery aspect. And then the second specification is once you actually offer discoverability for your capabilities, how you can actually offer secure ways of providing registration and connectivity access to that. That includes approvals. So a lot of times, especially with customer data, you enter what is like on our platform, you enter a sandbox mode. So you register, you don't get access to real data until you're vetted, or you go through some sort of registration process. In Texas, you have to submit your DUNS number, that sort of thing. So that is all possible within these capabilities, but it's an automated way of doing that. And then if there's any sort of notifications or profile management, that is built into the client registration protocol as well. So it's all kind of a batteries included sort of out of the box specification that if you are a utility and you need to provide data access or privileged data access for third-party entities and DERs, you could just tell them to use this protocol and they can just use that and they get the access that they need and you get to approve them when you need to. Okay, these are available on the website, carbondataspec.org. The individual working groups have subdomains. So this is connectivity.carbondataspec.org. The other one is customerdata.carbondataspec.org. And there are maintainer branches where you can read the drafts of these things. So these specifications are currently under development and review. The drafts are written. They're in GitHub, so it's all open. You don't have to get approval to start to read them. You can just go to the repository and read them. There are pull requests, so you can comment on them and everything like that. That's the beauty of the Linux Foundation, is that everything is encouraged to be very open and collaborative. You can go to the next slide. Can we show all the bullets on this? Apologies for doing it one by one. Okay, thank you. So a few key aspects of these specifications. Number one, we are not reinventing the wheel. We are building off of existing well-established specifications. Particularly for the discovery protocol, we are utilizing what is called the .well-known endpoint, and that is used widely in authorization or SSL endpoints. So the ACME protocol, it's used in OAuth, it's used in OpenID Connect, so single sign-on systems. We're basically just adding another well-known endpoint with a specified format. And so that's very easy for search engines and platforms to crawl and discover. And so that's a kind of a pre-built-in way of doing that. Secondly, the client registration. The client registration protocol is built off of the OAuth client registration protocol. So OAuth is a widely used standard for registering clients. It's used in finance, it's used in enterprise, it's used in healthcare, it's used pretty much everywhere for authorization protocols and token exchange. So it's basically an extension of that. There are both of these specifications in the connectivity working group are extensions of these very well established protocols that are used in other areas. What we do is we basically add on the utility specific or energy system specific components that are needed, as well as the profile management components that are needed. Let's see here. It offers high amount of customizability for the individual utilities or ISOs that are implementing these endpoints. And so if you have program specific requirements, you must be a certified this, you must do this, you must pay a certain amount of money. Those are all options that can be added to the data format. So that's included, so that you don't have to build your program around these protocols. You deploy the protocols to fit your program. Okay, and then the other thing that's really awesome about these is that the client registration aspects is designed to support multiple programs. And so you can register as a DER if you, say, are working with a utility to do some sort of demand response program and EV charging program and net metering program and some sort of like capacity contract. You can register using the same protocol and just get access to the different scopes in which you are approved or which you are participating in. And so you, as a utility, if you implement this sort of registration process, you can just tack on additional scopes as you build them out. You don't have to, you can just deploy it once for one small thing, get people onboarded for it. But then when you do another program, you don't have to do an entirely new onboarding process. And so this allows for gradual rollout of program implementations at scale. The next slide. Yeah, how they can be used by other protocols. We can go ahead and skip through this. I think I've talked a little bit about this. Keep going. So here's an example. Next slide. If we go to the, you can insert your other specification here, right? This is the adaptability or flexibility of these protocols. Go to the next slide. Next slide. So for example, a real-time market access could be specified here, or the next slide. Or next slide. The program participation APIs can be here. And you can do those in parallel. You don't have to deploy new endpoints for these client registration endpoints as a centralized entity. Okay, next slide. So there are 3 parts, and we can do 3 slides. One more, yep. There are 3 parts that are needed in order to extend these specifications for your own protocols. You need to define a capability that will be listed in the discovery endpoint. You need to define the scopes if there's client registration involved, the scopes that the client needs to register for, so access to the real-time market or something. And then thirdly, describe any metadata that is needed in order for the participant, the registrant, to figure out what's available. So links to online documentation, API endpoints that are specific to your protocol, that sort of thing. We can go to the next slide. Okay, so conclusion, what to know. Next. So this is the website. These are the active participants. The major participants are Google, Microsoft, and Apple. Utility API is a software vendor for utilities and DERs. So we're the maintainer of 2 of the working groups, but there are also Europeans involved. There's US companies involved. There's a whole bunch of folks involved. It's very exciting being a part of this working group. Next. These are the working groups. We can go to the next slide. These are the connectivity specifications. So we are solving the problem of scalably providing third-party companies a way to discover, register, and connect with utility and other central entity data programs, APIs, and other capabilities. It's a highly extensible and designed to be used by others beyond just the CDSC's own specifications, and will always be available as a free and open standards. Okay, go to the next slide. And the last slide. We need help. Join the mailing list, join the mailing list, join the mailing list. The specifications are open and available for review and comment. You do not have to join anything in order to comment or participate. If you do want to add a section to the specifications, there is a legal document that we need to have you sign that basically just says, this is not proprietary information, royalty-free, blah, blah, blah. And so standard open specification sort of documentation. But please, I encourage everybody to check them out and reach out to me or see what's up next. Our goal is to have the specifications stabilized by the end of the year and take them to ISO sometime early next year. So thank you, everybody, for the overview.
Thank you, Daniel. All right, reminder for folks that are online, y'all have been very quiet. So please put any questions that you have in the chat. And also, if you don't feel comfortable saying your question, you can put that in there. And then Aaron has said that he's happy to read them off. So please put whatever questions you have in the Q&A. So are there any questions in the room?
Hi, Will Frazier with Ncord. First of all, fantastic presentation. That seems like really impactful work and it was very clear. So thank you for that. A lot of the presentations so far in the conference have been focused around like broader power systems planning. And that's also, there's a big data scalability problem there. You know, you're bringing in climate data, you're doing clustering, you're bringing in power systems data. Some of it's secure, some of it's open source, et cetera. So what lessons do you think the planning community can learn from the work that you're doing here? Or is there some sort of initiative that the LF Energy Foundation is doing along those lines currently?
So for planning specifically?
Yeah.
So I believe there are some other analytics groups within LF Energy that are open source pieces of software that do planning or analysis related to that. The CDSC is mostly focused on operational scalability of actual systems and deployability. So I would say that while these working groups are probably like more focused on the operational deployment side of things, the other groups within LF Energy, and I don't know the names off the top of my head, but for example, there's a open source calculation system, I think it's called Open EE Meter, that focuses on taking, okay, this is your energy data before you install the piece of energy efficiency equipment, and this is it afterwards. This is what the impact was. That sort of thing is an example of another group within LF Energy that does focus more on the analytics and planning side of things.
Thank you. Any other questions in the room? And no online questions? Very clear. Thank you so much, Daniel. All right, and next up we have Brett Busfold from AEP, and his presentation is titled Increasing DER Operational Data and Telemetry. So thank you so much.
First off, thank you for putting this on, and thank you for all the other presenters. Excellent job. I'm here on behalf of, again, my name's Brett Busfold. I'm here on behalf of American Electric Power. Next slide. We're just for kind of rough stats about AEP. We are a public-owned utility. We provide power for 5.6 million customers across 11 states, operate across multiple RTOs, ISOs, 7 operating companies. We have an extensive generation, transmission, and distribution network out there, as well as, because we're talking about DERs, about 53,000 interconnected DERs, most customer owned. Next slide. So with all of these DERs, there's a need for data and telemetry. So how are we connecting to, we just heard about the connectivity of resources. Well, how are we connecting to these DERs? We're running into the same issues that a lot of other utilities, a lot of other people are seeing, is that connectivity is a challenge. So we have been very successful at operating the grid, specifically the distribution wires, with all of these DERs connected with minimal visibility for the vast majority of these. All of the residential DERs out there, we've had minimal visibility into those as far as operationally what they're doing. We really only look at telemetry on, we only have that real-time SCADA, those real-time SCADA values on larger DERs. And at those, we're really just seeing it at the, and oftentimes just at our point of interconnection. So not necessarily what the DER component's doing. If there's, we're using our traditional SCADA infrastructure and RTUs. So traditional technology that we've used for years, and we've historically interconnected with minimal consideration for future use cases. So a lot of the DERs that are interconnected today, we weren't thinking about aggregation. We weren't thinking about a lot of this, these future use cases as people were asking for to interconnect their solar, interconnect smaller DERs. So a lot of this, these DERs on the system have kind of minimal visibility, especially for net metered customers. Commercial and industrial customers may have a solar array that offsets some of their load. We might not be able to see kind of the true value of that load, of that generation component separate from the load. So a lot of this stuff we're seeing as at a net metered, in a net metered fashion. Next slide. This provides challenges, but we are making improvements towards kind of solving some of these issues. We have recently implemented a new technical DER technical interconnection and interoperability requirements. Those are system-wide. Up until then, we've kind of had more kind of per operating company or per state interconnection requirements. We're aligning, we have been, but we're continuing to align with IEEE 1547, 2018 for connectivity. And what we're looking at for the first time is interconnecting at the DER level instead of at the, just at the point of common coupling, or oftentimes a recloser or circuit breaker. So another thing we're implementing is an operational DERMS. So a DER management system that's going to provide us operational insights into what's going on the system. And that's alongside our advanced distribution management system, so our ADMS transition over the next couple of years. So those things are going to give us enhanced capabilities for situational awareness with all of these DERs, forecasting, things like that, that we haven't traditionally had. So those are some of the things that we have going on, and improvements we're making, but we do have a whole host of other capabilities that we're building out across our other entities, kind of with the other different groups within AEP. And I'm just focusing on like the operational data. Next slide. So some of the drivers for data and telemetry, making sure we have the right information for the people, technology, but the main driver is really the policy, the processes around this. FERC Order 2222 is clearly at the top of the list. It does a lot to give opportunity for a lot of these DERs, but it's really driven a lot of our internal conversations around this and pushed us to build out some capabilities. We need to be able to see these resources as individual resources, but also be able to see the aggregate response, and then, like I said, disaggregate and see the individual response of those resources as well, and the impact on the distribution wires. So that's something that is is a challenge. The one other component that has been mentioned before is the demand response component. We haven't really looked at that as DER. So that piece of the aggregation is going to be another piece that we're going to have to continue to work through and figure out how to see those components. Another piece is as we're hitting the as we have challenges of interconnections, being able to have flexibility in interconnections, so being able to provide options for people who are trying to interconnect and want to be able to interconnect without the additional costs of upgrades, system upgrades and such. So trying to think through those use cases as well. The people side, obviously our operators, they've done an excellent job keeping the lights on up until now, and really kind of giving them the right tools to make these decisions going forward, and being able to have that visibility going forward in the evolving grid. So we need to listen. We were listening to them, seeing what they need to see. Also, the transmission operators. So more and more we're needed to communicate. So being able to aggregate what DERs are on a given circuit at a given station bus, and being able to communicate that up to the transmission level so that they have visibility into these resources as well. That's going to be critical moving forward. And that's internal as well as possibly external, the RTOs and such. Then we have the technology. That's a driver as well. Making sure, as I mentioned, we have an ADMS DERMS platform, ADMS and a DERMS platform that are both come with their own capabilities and needs. So we need to make sure that we have all the right telemetry, all the right information for them to work properly and are fully functioning, get all the value out of them as we can. So some of the advanced applications with our ADMS platform include your volt var optimization, feeder reconfiguration, different things like that. So being able to fully leverage those moving forward. Next slide. So we really got to look at it from the whole picture, what all those different components need, and being able to set ourselves up for success for that. So again, the TIIR for the first time put a company-wide matrix together for what kind of telemetry we're going to need and where we're going to need it. So anything below all resources within the DERM system is going to be forecasted if we have no other capabilities. Beyond that, we're going to have telemetry at the DERs for anything above 200 kW, and then anything above 500 kW we'll have additionally we'll have telemetry and a SCADA switch, so oftentimes a recloser or a circuit breaker. So having those hard limits is going to give us additional telemetry that we haven't historically had. When you see how many DERs that we have interconnected, the challenge is not necessarily with the larger ones, it's going to be with all the smaller ones. So being able to have, there's going to be a lot of DERs that we're still not going to have visibility into because we have a lot of those that fall below that 200 kW threshold. Next slide. So when we're looking at what kind of telemetry we need, what kind of SCADA points, what kind of information we're needing to gather, we really started looking at some of the use cases. We have more use cases than these, but this is just a sample of some of the use cases we have. So in order to maintain safety, what kind of information do we need in order to be able to maintain the safety of the wires and be able to disable those DERs when needed, maintain real-time operational limits, be able to reduce that load, maintain that flexible interconnection, those special operating agreements, and then coordinating D-wires reliability. So being able to communicate some of the day ahead, being able to identify and communicate those day ahead constraints and really think through those. So those are some of the use cases for some of the added telemetry, some of the added data that we're going to need, operational data we need. Next slide. So transmission operators, we worked with our transmission counterparts within AEP and started looking at what kind of information we would need. So we're looking at forecasted, so they need both forecasted and real-time data. Within DERMS, we're looking at having some of the real-time data actually being calculated because we'll have real-time estimates of some of the values that we don't have telemetry to. We also have the meteorology and, like I said, the telemetry component of any devices we actually have telemetry to will give that data as well. There's a couple things that go along with that. Any of our large DERs, oftentimes they're participating in the market or offering some sort of grid services. Those we clearly have telemetry, have a full metering package on and such. But anything smaller, we're going to have to be able to aggregate that information up to a level that's usable for our transmission counterparts. So making sure that they have the information they need. Next slide. So as I mentioned, DERMS comes with its own kind of requirements. We're going to have information that it needs. So obviously going to support what the distribution operators need, what the transmission operators need, but then the advanced applications. So we're talking volt var control, power flow, being able to have accurate information within the power flow models, feeder reconfiguration, and then fault location, isolation, and system restoration. None of those things work well if you don't have accurate information. So being able to make sure we have the right information, accurate data coming in, and being able to, like I said, make sure the tools are fully functional. Next slide. So kind of after looking at all of this information, what came out of it, or what's coming out of it, is SCADA guidelines. So changing up making sure we are meeting our needs internally for all of the increased telemetry, support the current needs, and being able to evolve to the future use cases as we see fit. There's also an effort to work towards doing virtual RTUs and in order to support scalability and reduce costs. But really, it's important to stay open and be able to capture any of that information that in any way we can. I know with the ADMS DERMS implementation, key component that we're exploring is a module within our vendor that our vendor provides in order to get extra data and extra connectivity for some more of the aggregator resources. So next slide. And that's the next big component to this whole conversation is the aggregations, how we're going to be getting that information. Like I said, we have some integrations with future integrations planned with our DERMS platform, but there's going to be a lot of challenges with a lot of work kind of figuring out exactly what that needs to look like for information, at what level, how we're going to need that at, like I said, at various points in the software and in the technology in order to make sure we're getting the right information to the right people at the right time. Some of the considerations are how we communicate, obviously making sure we have the right protocols and such. The reliability, security, making sure that we have clearly we need secure and reliable data exchanges with any of these aggregators. modeling information, making sure it's reliable, and then making sure that we have the ability to get that information in a way that's both, especially we heard about multinodal, being able to recognize that, hey, this information, these aggregations can be across vast areas, but they can have localized impacts too. So making sure we recognize and can both look at the impact of these resources from a widespread viewpoint, but also from more of a localized viewpoint as well, being able to see them at that local level and see those local impacts. Next slide. So some key takeaways as we move forward. The telemetry and data enhancements will be an evolution, and it will take time to fully realize. So anything that's in the latest revision of our interconnection requirements really won't be fully realized for people interconnecting until for a couple years. And any resources that have already been interconnected, unless they have a major material modification, they aren't coming up to those requirements. So that's a challenge. We're going to always be looking at legacy resources, legacy interconnections. Secure and reliable data gathering is critical end to end for operating the DER enabled grid. So really making sure that we have secure connections, secure and reliable connections that should land on everybody on that chain of communication, that chain of connectivity. DER data and telemetry varies greatly based on size, location, asset type, interconnection date. So like I said, there's a lot of variabilities. There's a lot of nuances to DER connectivity, DER data, and information. And we really got to recognize that. And again, with us operating under as many states and as many RTOs, ISOs, really being able to understand and recognize all those nuances across the different requirements that they might have, things that we can and can't do in different jurisdictions. So making sure we stay open to and adaptable for all of those nuances as well. Next slide. And with that, open it up for questions.
Thank you, Brett.
Yep.
Round of applause. We're now going to turn to some questions. Folks online, once again, if you have a question, please put in the Q&A. And are there any questions in the room?
Yujie from MISO New England. Could you talk more about the virtual RTUs and how they're being used?
Yeah, so that is I wish I could give you a bunch of information on that. Really what we're looking at doing is working more towards centralized RTUs. So just connectivity out to the field and then coming into more of a central hub, in which case we would do the processing and capturing of the data at that point. We'll still probably use a lot of our similar RTU mapping and things like that, but just more at a central location instead of instead of having a dedicated RTU at each DER. So yeah, that's still, there's a team that's a new initiative. So we're just working through the details on that now. Yep. Thank you.
We're going to turn to an online question.
So we have one online question from Anonymous. It says, what role do you think telemetry has to play to make sure net zero goals for different states or regions are attained in the near future? And are we building the infrastructure for it?
So I think there's, with anything, I think there's challenges ahead of us. I think as an industry, we've been able to take on a lot of challenges. I think it does play a big role. We do need information. We do have connectivity that we need, but I think there's some ability to bridge those gaps with some of the operational forecasting. I think we can learn a lot through AMI that we haven't historically done. But I think even with AMI, a lot of DERs are co-located with customer load. So being able to, as we work through, I think there's going to be some learning that we can probably do on getting more accurate information from them and being able to kind of understand the difference between the load, even at a central, even at one point, hopefully being able to learn what the difference is and what that true DER contribution is. So I'm to answer your question, I think it does play a piece, but I think we will, especially on smaller resources that we don't have connectivity, I think we will find ways around it as an industry and learn from the operational forecasting, AMI, and all the pieces and have ways around it.
And I have one question. So I know AEP is in 11 states, has different jurisdictional rules, requirements that go with that. And I know you spoke a little bit about some of the different DERA data considerations, but specifically for integrating aggregations, what do you think some of the biggest challenges are for data availability? I know it's a big question, but
I think the first thing I think is going to be the connectivity, being able to get the information we need, day ahead, real time, in both scenarios, being able to, as I kind of mentioned, kind of disaggregate and then look at the impacts of that, and then really kind of figuring out the coordination of how do we relay those constraints back and making sure we are deconflicting where needed. I think a lot of that stuff right now, it's not a major issue, but as we move forward, it will be.
Thank you.
Yep.
Any other questions in the room?
Hi, Daniel, Utility API and LF Energy. I have two questions. The first one is for load management technologies that kind of don't need interconnection. They're just something a customer buys and has. How do you consider that in your DER classifications? And how do you consider that in your calculations for this sort of telemetry? Because there's not really an interconnection step so far as usually for those sort of technologies. And then secondly, as you get more telemetry and data from behind the meter, what are the privacy, consent, customer authorization considerations that you're doing as you are now taking on that liability of safeguarding that information that isn't part of your grid, but is outside in the world?
Yep. And when you say load management, are you talking like battery storage?
So if I'm Siemens and I sell a building management system to a big building and it's got smart load control and battery management, or not battery management, but like, heat pump management, all that sort of stuff. And it wants to offer it as a DER, load flexible capability to AEP. That's just something a customer buys because it saves them money, and it could have a sweetener of participating in grid stabilization. And so when in your 53,000 less than 200 kilowatt DERs, I'm guessing those building management systems are not counted in that, and
Correct.
Should they be?
Yeah, so that is correct. And I think that's going to be something that's going to have to be a consideration. Also, the demand response component, those types of things. How do we consider that? EVs, how do we consider those? So a lot of those components are things that we aren't currently considering within that number, but they very well probably ought to be and will be at some point, because they will be a contributing factor to some of these scenarios. And then what was your, privacy. So the good news and bad news is we don't have that problem now, because a lot of this data we aren't collecting from at that level. So obviously our customer data, we get customer data. We're being mindful of that. We follow scrutiny with all of that information. But as far as a lot of those resources, we aren't getting the real-time operational data on a lot of those resources. So it's just the large, oftentimes, like I said, oftentimes transmission connected, but also distribution connected DERs, and those resources are oftentimes got SCADA telemetry. So it's not quite the same issues that you're talking about.
Any other questions in the room? Any questions online? Oh, okay, yeah.
So we have one raised hand. There's no Q&A for it, but I'm gonna allow Michelle to talk. If you see this, Michelle, feel free to chime in. Okay, I'm willing to bet that it was accidental, but yeah.
Alrighty, with no more questions, thank you so much. Appreciate it.
Thank you.
And our next presenter is joining us virtually. And so just want to take a minute to see if Zhentong is online. And if so,
Yeah,
if we
I'm
could do a quick-
online.
Okay, great. And is your video on?
Yeah. No, I don't have the video. Can I share my screen now?
All right, we will be broadcasting your slides, and so if you'd like to advance to your next slide, then just let us know. But we have Zhentao Shore from Stevens Institute of Technology, and he will be presenting a real-time economic dispatch approach for wholesale energy market with multi-transmission node DER aggregation. So thank you, and take it away.
Yeah. Good day, everyone. It's my pleasure to share our work. I'm Cheung from the Stevens Institute of Technology. And our work focuses on the management of multi-transmissional node DER aggregations. And next slide. Our introduction includes file paths, the background mass formulations, the introduction to multi-node DER aggregation, and case study, as well as the summary. Please, next slide. First, it comes to the introduction of the background. The FERC has encouraged DERs to be aggregated and participate in the electricity wholesale market. And it requires establishing DER aggregations that as geographically broad as technically feasible. One crucial issue is addressing the distribution factors and the bidding parameters for the numerous DER aggregations. Okay, please, next slide. For the current research on DER aggregations in terms of locational requirements, there are 3 tabs which are single node DER aggregation, such as the virtual power plants, the distribution system operators. And the second type is the multi-node DER aggregation, mainly the distribution factor-based methods. The last one is the donor pricing, which is commonly applied in European electricity markets. Please, next slide. Here, a diagram is given to show the properties of the mentioned methods. We provide 2 indices. The one is the modeling accuracy, such as the model of transmissional constraints and locational marginal price. The other one is the computational efficiency for implementing the market clearing model. As you can see, the common single node DER aggregation has good model accuracy, but it is weak in computational benefits. Our work focuses on the multi-node DER aggregation with dynamic DF, which achieves good balance between model accuracy and computational efficiencies. Okay, please, next slide. Specifically, the multi-node DF aggregation can be further divided into static DF and dynamic DF. The static DF is under exploration of RTOs like MISO. And the advantage of static DF is that it is simple, but it is less accurate and can trigger LMP oscillation. This is why we would like to study the dynamic DF. Well, please, next slide. This slide gives a brief introduction on what is DF. An example is given here for illustration. At time t, if a DER aggregator has two DERs with one has an output of 1 megawatt and the second also have 1 megawatt, then the DF for the two DERs are 0.5 and 0.5. At time t+1, the DRA has the first DER of 1 megawatt and the second of 2 megawatt. Then the DF becomes 0.67 and 0.33. It can be seen that each DER is labeled with a DF, and all DF under a DERA are summed to 1. Okay, next slide. We introduced the real-time economic dispatch with DF in this slide. The regional transmission operator performed the RTED with DF, and DF is preset according to DF updating strategy. The instructions is sent to the DRA, and the DRA is able to dispatch its underlying DRs. The advantage of this framework includes guaranteed computational efficiency with numerous bidding parameters. The difficulty of this framework is that how to capture the DF accurately and how to guarantee transmission safety when the DF are inaccurate. Okay, next slide. Here comes to the mass formulation part. Well, please, next slide. First, we give the mass form of DF. We define the DF with 3 types of constraints. First, the basic constraints, which require the DF under a DRA are summed to 1, and the DF should be non-negative. The second type is indicate a special situation when the DRA is shut down, that all the DF under a DRA are 0. The third is an implicit limit to ensure the estimate DF won't exceed the DER capacity. As you can see these 3 tabs on the slide. Okay, please, next slide. This slide gives the RTED formulation, including the objective, minimize the total operational cost. The costs are modeled in piecewise linear forms, which are benefit for the computation. Next is the power balance constraints. And the next one is the transmissional constraints established with power transfer distribution factors, as well as the introduced DF. Finally are the capacity constraints for generators and the DRA respectively. Okay, next slide. This slide shows the self-dispatch problem for each DRA. It can be seen that in the self-dispatch problem, the DRs are considered as controllable generation units. And it assumes that the DRA must follow the RTO's command. The self-dispatch doesn't consider transmission constraints. In our framework, we assume the DRA can dispatch its DER freely as it is want. Okay, please, next slide. This part, we explain how we implement the dynamic DF. Please, next slide. The proposed DF updating strategy has a predictor and a corrector. We also design a transmission signal for guaranteeing transmission constraints. As you can see, the system information and available data are given to the predictor, and it will gives the DF, and the DF will be corrected by the PID corrector. Then the final DF, which has a high quality output. The transmission signals are a series of formulas that we defined to contain the system information. And this transmission signal is calculated by the RTO and sent to the DRA. Okay, please, next slide. In this slide, we introduce how we implement the predictor. We give two methods to implement the predictor. The first is the deep neural network, DNN method. We design the input features and predict the output of DER, and then the DER output are converted to the specific DF. We use the features including the mirrored output of DER for former terms and the nodal load as well as the total load. This data can be obtained by real measurement and can also be simulated by some models. The advantage of the DN predictor is that it has a good performance, but the disadvantage is that the DNN requires high quality training data. Okay, please, next slide. Here we come to the second method for implementing the predictor. For engineer application, we use a KN method to replace the DN. This is because the KN has a clear physical meaning and it is easy to implement and easy to maintain. The data labels are similar to the DN, and the advantage of the KN method is that it is easily to obtain the data and it can learn from the new data. The disadvantage includes that it may be sensitive to the outliers. Okay, please, next slide. This slide shows the timeline of how the RTO implements the RTD. At each time, the RTO decide the DF first according to the provided DF updating strategy. Use this DF, they can perform the RTD. This DF-based RTD is reduce the score and can be performed efficiently. And this framework, this timeline framework is rolling. One time print and one time after one time. Okay, please, next slide. After the predictor, we also add a PID-based corrector to further improve the performance of the DF. The KM predictor can be improved by using PID controller. This controller, also known as the corrector, uses the prediction errors as the input signal and corrects the DF errors. In our test, we found that the most relevant parameters are the P parameter and I parameter, while the D parameter is always 0. Okay, please, next slide. This slide gives the mass form of the transmission signals. The transmission signals are calculated by the RTO and transferred to the DRA. The transmission signals help the DRA to share the responsibility of transmission security. The transmission signals are compact form of the system information. which won't share private information to DRA. Yeah, please, next slide. With the transmission signal, the self-dispatch problem for each DRA is augmented. As you can see, the self-dispatch problem now includes the objective for minimize the operational cost, the power balance to ensure the RTO's command be guaranteed, and the capacity of each DER. The last one is the transmission constraints that should be considered by the DRA. Okay, please, next slide. Well, we also proved that the proposed transmission signals form a sufficient condition to guarantee the transmission constraints. And the proof detail is a little complex, and we won't explain it detailed. If you're curious about that, you can email us and discuss it. Okay, thank you. Please, next slide. Oh, here comes to the test results with the above enhancements. We test the real-time economic dispatch. Yes, please, next slide. We performed tests on modified IEEE 118 bus system with 26 DRAs, and each DRA contains more than 3 DRs. Each DRA bids for at least 3 segments. The DR capacity occupies about 83.6% to the peak load demand. Okay, please, next slide. One crucial thing is that the DRA will bid for numerous bidding parameters. In our test, we use the piecewise curves for the bidding. As you can see, if a DRA has 3 DRs, the capacity and the cost are shown in the table. And in this case, we'll give it a 3-piece bidding curves. Okay, thank you. Next slide. We first show the test result on LMP errors. This is an index to show how the model, to show the accuracy of the model. As you can see, the proposed method shows a similar accuracy to the single node DR aggregation. Well, it also has evident advantages compared to the fixed DF and Juno pricing method. And this is how the LMP error calculated. It is the absolute value of the settlement LMP to minus the dispatched LMP. Okay, please, next slide. The second index is the solution time, which indicates the computational efficiency. The proposed dynamic DF has a shorter solution time compared to the single node DR aggregation, and it shows relatively good solution efficiency. Compared to the fixed DF, the dynamic DF has more solution time, but the incremental is not obvious. Well, it is increase the solution time of the dynamic DF method reduced about 40% compared to the single node one. Okay, please, next slide. In this slide, we use the LMP congestion to verify the effectiveness of the proposed transmission signal. As we introduce the transmission signals, all the results of the RTD dispatch do not have transmission violations. So we use the LMP to evaluate the performance. If the LMP congestion is large, then the aggregation method may push more pressure on the transmission. As you can see, the proposed method show good performance in relieving transmission congestions. The result of the dynamic DF is very similar to the single node aggregation, and it shows evident advantage compared to the fixed DF and the dual node pressing. Okay, please, next slide. From the test results, it can be concluded that the proposed multi-node dynamic DF strategy provides a good balance between solution accuracy and solution time. It is as accurate as single node DR aggregation and as efficient as dual node pressing method. While the introduced transmission signals are effective in relieving the transmission congestions. Okay, please, next slide. Here comes to the end of our report or of our introduction. We gave a summary here. Okay, please, next slide. It is summarized that the proposed dynamic DF updating strategy performs relatively well in accuracy and efficiency balance. The transmission signals are effective in guaranteeing transmission constraints, and the proposed method offers an effective approach for DR aggregations in electricity market participation. Okay, that's all. Please, next slide. Well, that's all. Thank you for your listening. Thank you.
Thank you. All right, are there any questions in the room for our presenter?
Yujie from ISO New England. I have a question about the settlement LMP versus the dispatch LMP. You measured the error between them. Could you give more details? Is the settlement LMP the ex-post LMP considering some deviation in following the dispatch signals? Thank you.
Okay. Do you mean that how can we calculate the settlement LMP?
Yes.
We just simulate and let me see. Oh yeah, we first we do the real-time economic dispatch, and after we solve the solution, we put them into the dispatch model again and calculate the LMP to serve as the settled LMP. This may different from the real application, but well, we use it in our simulation and our test.
So why would they be different? I guess that's a part I didn't fully understand. If you solve the dispatch signals, you give it to DRA, and will they perfectly follow the dispatch signal?
Oh, okay. Yeah. Well, we actually do a settlement dispatch model for the system without DR aggregation. The method, the proposed method is actually for decrease the solution time. When we calculate the settlement LMP, we do not consider the time, and it's so a big model that can include all accurate DR information. While the others one, like the single node DR aggregation and multi-node DR aggregation, all have or smaller. This means the settlement LMP is without the DR aggregation, and the dispatched LMP is with different aggregation methods.
Thank you.
Okay, thank you. Thank you.
Questions? Okay.
So we have one question from Jai. I'm right now unmuting you if you would like to ask it yourself.
Hello, can you hear me?
Yeah, we can hear you.
Yeah. So yeah. First, the presentation is pretty complete. Very good from end to end with formulation with the test. Right, it's good. At least you have the experience about the dynamic factor. I have a question about is the method was designed to working for both homogeneous DERA or and heterogeneous, or have assumption, because the question is probably related to your formulation 2.2, the basic tricks, Fe had to be greater than 0. My vision is like you have PV, right? You have battery, right? For example, battery charging will be negative megawatt, right? So withdraw, then you have positive. In that sense, the factor. If you look at the general megawatt example you put there, right? It's more like a positive negative. In that sense, you have we have negative 1, positive 1, right? What's your thinking? Is that possible? The method can be generalized for that, in future. So yeah, just try to understand your thinking, behind that.
Yeah, well, actually, in our current framework, we do not consider the details of the DERs. We just assume that the DER is a controllable unit that can be output from 0 to its capacity. We do this assumption based on that we treat the DER as a transmissional node level DER, such as a virtual power plant. It already aggregated the specific DER to a single one, and it projected the DER to the transmission node, and we just manage the DER on the transmission node. That means we actually introduced a second level management. A second management level. The specific DER to be aggregated to a transmissional node level DER, and then we use the DF to capture the transmissional node DER, and the DRA is further to aggregate the large DF, the controllable DF, to bidding in the electricity market. Well, in the future, we may consider the details of the DR. Our current assumption is relatively strong for some DR like storage. Actually, the storage can be positive and negative in terms of nodal injections. Yes, that is.
Okay, thank you. Because for the formulation, right, even for the implicit DL limits, right, you also have kind of a assumption the max had to be positive, right? Otherwise, the equation doesn't hold, right? So anyway, yeah, just a comment. Yeah, I understand. So it's a good first step. Thank you. Yeah.
Thank you. Thank you.
Are there any other questions in the room? And any more online questions? All right, well, with that, another round of applause for our speaker. Thank you so much.
Okay, thank you.
And for folks in the room, we're gonna now go on a break. And so the next set of panels begin at 3 o'clock. So you'll have a little bit of extra time here in the break. I know the last panel of the day is pretty long. I know it's a long day, lots to take in. And so definitely encourage folks to get up and move around during the break. So we'll be back then, and thanks y'all so much.
Right. Good afternoon, everybody. We're going to start session WA3. Our first presenter today is Wei-Han Ren, and they're presenting bidding strategies for battery energy storage, addressing uncertain market clearance patterns. You can take it away.
Good afternoon, everyone. My name is Wei-Han. I'm a third-year PhD student from University of Florida, and here presenting our work with Dr. Guan and Buck. And next slide, please. Okay. Battery energy storage is a very hot topic right now because of the large integration around the world, and it's traditionally considered as a reserve purpose for frequency market to smooth the variations in energy supplies. And according to California ISO, the total battery energy storage by 2024 is at a capacity of more than 10,000 megawatts. And in about 20 years, by 2045, they project the energy storage to be more than 50,000 megawatts. So it's there's more than enough, probably not enough, but there's a lot of energy storage on the market, and more and more people use it to do the energy arbitrage, which is buy and sell the electricity and make profits from it, as well as providing the energy to the market. Next slide, please. However, the existing bidding strategies from the literature, they usually use dynamic programming or Markov chain decision methods. And however, these methods are not cannot completely capture the arbitrage pattern in the practical data, as we show later. And this is caused by the complicated scheduling model at the ISOs. And many private battery owners also want the scalable and robust bidding strategies that which is lacked right now in the literature. Next slide, please. So first, we need to understand how can a battery owner to participate in this energy arbitrage market. According to the market rules, a battery owner can submit a battery bid 1 day before the market in the day-ahead market. Here's a plot of the real-time energy price. Next slide, please. The battery owner can submit a bid, which consists of a bid price and offer price, as shown here. The green line the green line here is the offer price, which means the battery can be charged when the price fall below this price threshold. And the red line here is the offer price, which means when the energy price is higher than this line, the battery can be discharged to make profit. Next slide, please. So here, the green triangle indicates where the battery can be charged, which is when the price is lower than the bid price. And the red triangle is where the battery can be discharged to make profit. Next slide, please. However, the market clearing pattern is not certain. Unlike stock markets, which we mostly understand by our instinct, is that as soon as the price fall below the threshold, we can make this deal. But according to the real data, the clearing usually happens at any time. So here we summarized 3 models to capture this uncertainty. The first one is called best case model, where the battery is charged at the lowest price possible, and then discharged at highest price, so that the battery owner will make the most profit through buy and sell. The middle plot is the first price model, where we assume when the market gets very competitive, then there's all kinds of battery bids. So as soon as the price fall below your bids, your battery can be charged. You can purchase electricity from the market, and then as soon as the electricity price is higher than the offer price, you are able to sell. So that's called the first price model. This third one is called random case model. We assume that as during the interval that the price is lower the offer the bid price, and the charge can happen at with the same probability at each time point, and same as the sell period. So this is we would call it random case model. Next slide, please. So that's the uncertainty in the market, and we also have different ways to bid. The most simple one is that we can submit our bid as consists of two prices. One price is a bid price, another price is offer price. With this price will stay the same during the course of the day in the real-time market. The second way is we can submit 24 pairs of bids. So which means that for each hour we can submit a different price, which can show our different expectations of the energy price at different time interval. And the last case is self-scheduling, where we don't care about the price. We just charge and discharge at fixed time during the day. For example, here we show that at 5 a.m. and 15 with 3 p.m. We charge our battery and we empty our battery at 10 a.m. and 8 p.m. Next slide, please. So we first created a basic model to show how this market works. The objective is to maximize the profit from the battery owner's perspective, which is market clearing price, PT, times the amount of energy you charge or discharge, which is WT, plus or minus. Then there's inventory constraints. We assume that at the beginning, the battery state of charge is 0, and then you can charge or discharge through WT. Next is the price constraints. So here, ZT plus and ZT minus are binary variables. ZT plus equals 1 is when we charge our battery. So this happens when the LMP, or the energy price, is lower than our bid price, it's fall below the green line. The second one is discharge indicator of ZT minus. The discharge happens when the electricity price is higher than the offer price, higher than the red line. And last one is charging and discharging boundaries, where capital C is battery capacity, and eta is battery efficiency. For example, when the eta is 90%, which means when you purchase 10 megawatts to your battery charge your battery will only end up at 9 megawatts. So eta is battery efficiency, and ZT is charge or discharge indicator. And here are the main constraints for the model, and the actual model will consider charge and discharge cannot happen at the same time, and there are also the charge price and discharge price. So the charge price must be lower than the discharge price to make profit. Next slide, please. So with we also built so the previous was a basic model, and we also add some logic constraints to formulate the model of the first price model and the random case model. However, we that two models will add too many binary variables to mimic how the market works, and then the model becomes very hard to solve. To make our model solve more efficiently, we create this network flow reformulation, where we split the 24-hour day into 3 types of time intervals, as we show here: the green dots, blue dots, and the red dots. The 3 types of period are buy period, sell period, and idle period. For example, at the period 0 to 4, all prices are below the bid price. So that is the interval where we can buy the electricity. And this is a buy period. Next one at 5 a.m., the dot is the idle period because it's in between the offer price and bid price. So there will be nothing happen. And in this way, we will know that at each time point, there can only be one type of period that this time period belong to. So we can communicate this dots different time period together, and we can treat each time period as a node, and the connection is shown here as a flow conservation constraint. So at time point j, all time interval that comes to j, like xij, yij, zij for all the I before j, and will equal to the next period of bidding types, charge or discharge types. And the objective is similar, but here the P has two subscripts, I and J. Previously, it's only have one period, one subscripts. And because this PIJ will be used to indicate the price, the clearing price that happens during time interval IJ. Next slide, please. So there's also a very good benefit from this formulation is that by simply changing the objective PIJ, we can generalize the three cases we showed before: best case, first price case, and random case. We just need for the best case, we just need to use the maximum PIJ on the discharge interval and minimum PIJ on the buying period. For the first price case, we just need to use the first price during each IJ period. And during the random case, we just need to use the average price on this IJ period. So in this way, this model not only can be solved faster than the previous model, and also generalize three situations. Next slide, please. Yeah, so that's our model, and we did our case study on the CAISO data. We use the data from January 2020 on 3 buses. We have 2 trading mode. The first trading mode is a one-time validation, which means that we use the data to the first 15 days of January data to generate our bidding strategies, the bid and offer prices, and then we'll apply the phased bidding strategy on the rest 15 days of January, 16 days of January. Next slide, please. So before we show the result, we were expecting that self-scheduling should be the best because it's not the price is not related. We were just optimized based on the time. So self-scheduling should be the optimal way to identify the best time to charge and discharge because it has no interference with the price. And however, on the first 15 samples, we can see that the self-scheduling is not as good as others. So on this heat map, each column is a result from a bus, and each row is a different strategy. The top 3 rows are best, first, and random strategy with single bid. And the next 3 rows, best 24, first 24, random 24, are the 3 models with coupled with 24 pairs of bids during the day. And here, from the training result, we can see that random 24 and first 24, best 24, and best are all pretty good. And but we want to apply these 7 methods strategies on all 3 different market situations. So next slide, please. So here is a separate result of validation result from 3 buses. For example, let's say the first one, it shows the strategy was applied on 3 columns. The first one is in the setting of best market, and the second one is the first price market, and third one is the random case market. And as shown here, the self-scheduling, because it has no barrier of the price consideration, so it has the highest profit. And in the best market, the best 24 is the best strategy. But across all three situations, we can find that random case 24 performs the best. Next slide, please. The second trending mode is the rolling horizon validation. That for example, in the first test, we generate our bidding strategy on the first 15 days and test only this strategy on the 16th day. And next, we use January 2nd to January 16th days data to generate our strategy, and use the strategy on the January 17th day. So this is called a rolling horizon validation. Next slide, please. Here we show the performance of each strategy, as well as we also show the upper bound of the profit that you can get from the market. The first we can focus on the first plot, which shows the result from the best one. That still self-scheduling is also shows a very good result. And the second place, the red bar is the average across 3 market situations. The blue, which are the blue bars from the best case, first price case, and random case. But we can still find that random case 24 is also the best under the self-schedule method. And we can also notice that the first price 24 is also pretty good, because it's considered the situation, kind of worst situation in the market, that it the market clearing happened at the first price. Next slide, please. So here are the more detailed performance on each day. There's the next slide, please. And yeah, the previous slide, most plots has a negative returns, while self-scheduling always have positive return because of specialty. And next slide. Yeah, so we also notice that the rolling horizon validation generally has better results than the one-time validation. This happens because one-time validation keeps the strategy unchanged during the rest of days. However, as we can see, the blue lines are the previous 15 days energy price, and the red line is the current day's energy price. For example, on day 25, the red line denotes the energy price on day 25, and the blue lines denotes the previous 15 days energy price. We can see that almost all the energy price on day 25 is above the day 25 energy price. So this will make the bidding strategy just use previous 15 days data very vulnerable. Next slide, please. So the takeaway is that the first 24 and random 24 methods are very robust in handling different market uncertainties. And self-scheduling is consistent, stable performance, but it's not very realistic because it didn't consider the price. And further improvement, we can consider larger data set to compensate for the delimitation of the effective of the data. And we can also try to improve the model that used in ISO with a large scale energy storage. Yeah, thank you. That's it.
Right. Do we have any questions in the room for our presenter?
Yeah, this is Bing from RIT. I have a few questions. So first one is related to the base formulation.
Yeah.
So you have two binary variables, the charging and discharging.
Yeah.
And then do you require them to be like they cannot be one at the same time, right?
Yeah.
Yeah. And also for the inventory that equation, do you have a limit on I? That is like a SOC max. You don't have a SOC max?
No, because W is limited and I is plus W and minus W minus. So W is limited by the capacity, by the SOC max.
SOC max,
yeah,
but it will keep charging.
If it's we omitted the charging requirement constraints, so you can only charge when the battery is not full and the price is appropriate.
I see. So that one is changing. Okay.
Yeah.
Yeah. Second question is on the new model. The new model, you have 3 binary variables. So that's a good idea to have this the different period.
Yeah.
So I have a quick question. For example, if X like 2, 4 is 1, means it's a selling period from like hour 2 to hour 4.
Yes.
So does this mean X2, 3 and X3, 4, they are all both 1?
No,
They will be
they'll be 0. So at each one 10 point. So for example, at 10.2, alpha and beta plus gamma, X plus Y plus Z only equals to 1.
Okay, so if X2, 4 is 1, that means the battery is charging for the 3 hours from 2 to 4.
Yeah, the charging could happen during any time point.
I see. I actually have one more question related to the random one. So you use the average price. So can you explain more about why you're using this average price for the random ones?
Yeah, in the random case, we assume that it's a uniform distribution when the charge happens on this period. So we just use the average price as a random case price.
I see. So you have this assumption. Okay.
Yeah.
Thank you.
Okay.
Alex Rutkiewicz, Newton Energy Group. Your trading assessment is based on the assumption that storage bidding doesn't affect the price.
Yes.
What if it does?
Yeah, it could be when there are a lot of market participants and they optimize on their own.
They all use the same algorithm, right?
Yes. So in our model, we assume all the battery owner is just a price taker, so it does not affect the market price. So
no, it does not. Well, it's a price taker, right? But the price actually may be affected. It just doesn't intend to do that. But
yeah, it could be a future injection.
Right. Great.
Hi, thank you so much. So, excuse me. From a regulatory standpoint, are there any issues with the self-schedule strategy, or would it be worst case the bid just gets rejected or doesn't get fulfilled for most ISOs to generalize?
The worst case is that your battery can be charged to full capacity and then you never get discharged. So you will never make profit from it. So that's the worst.
Okay, great. And I think we're going to go to one question that is from the online group.
Yeah, we have an online question from Anshul. I'm just allowing you to talk, Anshul, if you want to hop on.
Hello, am I audible enough?
Yep, we can hear you.
Yep, this is Anshul from University of Waterloo. I just had a question that do your model also incorporate different C rate, heterogeneity of BESS? If they have different C rate, then how does the bid and offer characteristics change?
Do you mean different batteries?
Different C rate of the batteries, like 2-hour, 4-hour BESS.
I think that could be including our 24 pairs of bidding strategies, because if there's a better there's a better objective value for some period, like 2 consecutive period have the same bid price, that will be one of the solution in our 24 pairs solution. And does that answer your question?
Yeah, partially. I just wanted to clarify that if there are that consecutive periods make sense, but how to differentiate whether when you have a, like if any BESS owner has 2 hour and a 4 hour battery, so based on your second model, which you have classified into 3 periods, it can have different bids and offers, considering if at consecutive periods for charging, then it might consider higher duration battery for charging at that time. Similarly, during the discharging period, correct?
Yes, yes. Thank you for the comment.
Okay.
Okay, we have time for one more question. Are there any questions in the room? Great.
Yeah, just short comments. This is Kwok from University of Florida. So I guess the one short comment is about the motivation for this research. Because we work with market participants, to submit the offers, battery offers to participate CAISO market. At the very beginning, we thought everything would be clear, in time. We submit the offer, and then as long as the price is lower than the bidding price, we should be able to buy. And as long as the price is higher than we offer price, we should be able to sell. But the actual, I think yesterday, CAISO, they mentioned about the battery storage because there's so many battery storage in the market, and those energy storage cannot be clear in time. So basically, we observe that actually those patterns, when we submit the offers, it will be clear, like during this we call charge interval, can be clear anytime, in this like from 2 to 4, and then we look at this historical data, basically uniform distributed. So essentially, the bottom line is when we do bidding, we cannot rely on this. Okay, we as long as we meet the offer, and then we meet the price, we'll get the offer accepted or get paid or not. So therefore, we really need to consider random case. So that's kind of comment for motivation. And in terms of another question about if the battery charge like instead of 1 hour into multiple hours, because some like a containerized battery, they take like 2 hours, 3 hours to charge the charge. So this model will handle that as well because time limit, we cannot give the details. Yeah, thank you.
All right, let's give one round of applause for speakers. Okay, and our next presentation will be a joint presentation between Sasun Asataran and Nitun Madhaban. The presentation is entitled Integrating Battery Storage into Electricity Markets, Accounting for Degradation Costs and Participation Models in IESO Wholesale Markets. And are you starting first? And then Sasun will be starting first.
I just want to make sure you guys could hear and see me okay.
Yep, yes. All good.
Okay, perfect. Yeah. So I'm going to get started and then hand it off to Nitin. Good afternoon, everyone. I'd like to thank FERC for the opportunity to present today, and my apologies for not being able to attend in person. My name is Sasun Asaturian. I'm a lead for the Innovation Research and Development Group at the IESO in Toronto, Ontario, Canada. My colleagues in this study are Nitin Padmanabhan and Eric Ela from EPRI and Bo Yuan from Cornell. Nitin and Bo are attending in person, and together we are presenting our study on integrating energy storage, accounting for battery degradation costs and different participation models into the IESO markets. Move to the next slide, please. Just as a general overview of the presentation, I'm going to be giving the introduction where I talk about the project background, the motivation and goals, and then I'm going to be handing it off to Nitin, who will be discussing the research aspect of battery degradation modeling, the mechanics of how to account for battery degradation into different storage offer modules, and then he will present a summary of our study results and the overall conclusions of the study. Next slide. One more, please. Yeah. Okay. I don't think I need to. Oh, sorry. If you could go back one more. Yes, this one. Thank you. I don't think I need to explain to anyone attending this conference about the proliferation of storage across the electricity sector. In Ontario specifically, we're a little bit behind a lot of our US counterparts. It's only more recently, over the last year to year and a half, that we've contracted almost 3,000 megawatts of standalone storage resources. that are expected to connect over the next 5 years and participate in our wholesale markets. The key questions of concern for the IESO and perhaps some other US jurisdictions that have already heavily adopted storage. What is the value of storage state of charge management? How do we accurately assess the capacity valuation of storage? What are the impacts of battery degradation on storage profitability and market efficiency? This study, which focuses on battery degradation and different storage participation models, hopes to shed light on some of these questions. Next slide, please. Diving into more detail, the IESO has a system capacity need that's emerging towards the latter half of this decade. To meet this need, we've contracted almost 3,000 megawatts of standalone storage capacity. The IESO has two different storage participation models, a basic interim storage model where we model storage with a separate load and a separate generator resource at the same node, with separate bids from the load resource and separate offers from the generator resource. This resource offers no state of charge management construct. State of charge is managed by the storage resource themselves through their bids and their offers. We have also conceptualized, but not yet implemented, a more sophisticated enduring storage model where we have a new single storage resource that could both inject and withdraw at the same site, that participates in markets through one continuous bid offer curve and also offers an IESO managed state of charge construct to ensure feasible dispatch and better storage optimization. With this in mind, the motivation and goals of this study for the IESO were twofold. First, we wanted to help quantify the market efficiency and system reliability benefits of moving from our interim storage model to the more sophisticated enduring storage model. Secondly, we wanted to determine the impacts of modeling battery degradation on those benefits. Next slide, please. Nitin will dive into the study details a bit more, but this slide serves as a general overview for how the study was completed. EPRI used the Power System Optimizer PSO tool to model an accurate representation of the IESO's late 2020 system conditions, and then ran a production cost model to calculate unit commitment and market clearing prices on an interval by interval basis across a full simulation year. For this study, EPRI developed bid and offer modules for almost 2,500 megawatts of assumed standalone storage facilities under different 2-hour, 4-hour, and 8-hour battery duration sensitivities. They then further refined these modules into bid offer curves that were battery degradation aware or degradation unaware, and then finally mapped the modules to the two different participation models we were evaluating, our interim storage model and our enduring storage model. The end result were different sets of simulations that could be compared to one another to gain insights on the value of the different participation models and the overall impacts of battery degradation modeling. And with that, I'm going to hand it off to Nitin for his part of the presentation.
Thank you, Sassoon. So I'll take over and then I'll walk you through like some of the more details of like how did we model degradation, how did we implement it in the offer generation module which we developed. Next slide, please. So before doing that, I thought it would be good to have a high-level overview of the battery degradation process as such. So next slide, please. So actually, it's understood like the battery degradation mechanism has a significant impact on the operational cost of the BES. Now, accounting the degradation cost is within the power system is very crucial to ensure the economic utilization of these resources and to make sure that these provide a fair return of investment to the investors. So the degradation typically can be broadly classified into two, the aging, which is the cyclic degradation and the calendar degradation. When we are talking in terms of short-term operation of electricity markets, so it is basically the cyclic degradation, which plays a significant role. So the various factors on which the degradation depends on is the state of charge or the depth of discharge, the discharge rate, temperature, etc. So there are a few factors which are very crucial, like say, for example, depth of discharge. right? So depth of discharge, how it plays a role is, the figure on the bottom left shows, like based on depth of discharge, the higher the depth of discharge, it has more impact on the number of cycles. So the number of cycles that we can get from a battery reduces considerably. Similarly, if you on the right side, what we see is the impact on the life loss when we consider the discharge rate. So as the discharge rate increases, so that also decreases or has a higher impact on the life loss. Now, when we talk about depth of discharge, another aspect is so just not the value, how much depth the battery is discharged. So from where to where? So what was the initial state of charge the battery was? So for example, a battery which was at 80% state of charge, and if it discharges to 50%, so depth is 30% depth of discharge. But if the same battery discharges from 60% state of charge to 30%, still the depth is 30, but the impact of degradation in these two cases is different. That is, so when you start at 80 and go to 50, or whether you start at 60 to 30, the degradation is more severe in the second case. So that is important to understand. Also, so the one thing is how deep you discharge the battery. The second thing is how fast you discharge the battery. You discharge, say for same example, 30% discharge. Do you do it in 1 hour, 15 minutes, or 5 minutes? So that also makes a huge difference. So these aspects are needed to be captured. So the FERC Order 841, it mentioned that the limited energy resources, when they submit their bids and offers, it should actually capture the physical and operational characteristics. So this is what we believe, like why the degradation is an important factor which has to be captured in the bids and offers. So in the literature, there are various ways this has been done, various approaches. I'm not going to details of it. So there are 5 different ways in which broadly we can do this. And yeah, going for in this approach, in this study, what we have done, may I go to the next slide, please? We have adopted the method of what we call the rain flow algorithm method. So the rain flow algorithm, this was basically used for fatigue analysis, but lately it has found good application in actually dividing the cycles, decomposing the cycles. If we know the state of charge of the battery, it can be divided, and then we can capture degradation out of it. So if we have a profile, if you look into the figure on the right side, if we have a state of charge profile like this, and then using the rain flow algorithm, we can identify the half cycles and the full cycles. What has been shown, I understand it's a little difficult for you to see. So if we, so with the depth, so there are basically 3 points we have shown with a depth of 10%, which is a half cycle, and the one with 40% depth, a full cycle. So if this depth cycles are identified, then we can actually, using a cost function, come up with a degradation cost for this battery. And this, in the previous figure, when we saw actually the relationship between the depth of discharge rate on the life is non-linear. So it would be difficult to use a non-linear function in your market models. So this can be linearized. So what we see here is a linearized version, piecewise linear version of the cost. So this cost, piecewise cost corresponding to different depths. So on the figure on the right bottom, we see if we have that function, we can divide it into segments we like. It can be divided 2, 4, or 16, right? And based on those corresponding depths, there is a cost associated that can be used in the as a degradation cost. So this is basically the idea what we have used. Next slide, please. So next, I'll walk you through like the offer generation module, what we have developed based on the degradation cost, which we included in this offer module generation model. So next slide, please. So this gives a high-level overview of the storage of offer generation module. So the important components, what we see is inputs, the core optimization, and then the output. So on the input which goes into this offer module is basically the prices, the market prices, if the battery storage knows the market prices. And of course, there would be uncertainties which have to be accounted. So that we do using scenarios. And then we need to know the battery characteristics and the degradation cost components. So these go as input into the offer module, which is actually an optimization problem, which maximizes the expected profit of the storage, subject to the operational constraints, considering the market rules, the risk, accounting the risk, etc. So with the outcome of this optimization problem is what we get the offers generated. So the offers for the storage can be generated, and that's the output, right? And next slide, please. So another important modeling approach what we used here is, so we were using these offers in the production cost model, right? So it's actually we wanted to replicate that human behavior. So when a participant, a storage would participate in the market, there would be changes in the market condition from day to day, right? But in the production cost model, how do you do that? So for that, what we proposed is we divided the state of charge of the battery into 7 bands. We can do as much as we want. So here what we did is, say if you see 7 bands, band 1 is when the state of charge of the battery is between 0 to 5%. The next band being 5 to 20, 20 to 40, so on, and the last between 95 to 100. So if the battery starts at whatever value in that band, so considering that and the market prices, the offer curves were generated. So basically what we are doing, assuming the battery is at so and so level among one of the bands, and based on that, what would be its offer strategy. So we have 7 sets of offer generated for each hour for the battery resource. And when we input this into the production cost model, so based on the state of charge, which is determined on the previous day noon, so what is the state of charge, the anticipated state of charge? So corresponding to that state of charge, the offer curve is selected. So this actually helps to mimic the human behavior. This is what we thought is an important contribution to. Next slide, please. So this shows a sample offer curve for which, so what we see in blue is the degradation unaware. So when degradation is not accounted, and what we see in the orange color is the degradation aware or degradation accounted offer curve. So we are showing it for 2 sample cases. One when it's like a discharge offer, and what we see on the right side is the charging bit. So what we see is, as a result of accounting degradation, we understand additional cost is assigned, so which results in the BS degradation offer prices are basically higher than the higher prices for discharging, and it bids a lower price for charging. And so it is willing to discharge or charge at different quantity given the same price points. So this is what happens when we account for degradation. Next slide, please. Now I'll present a summary of our results. Before that, next slide, please. So we validated the offer curves we generated, degradation of our offer curves on the IESO system, the Ontario system, which has a peak demand of about 25.6 gigawatt. And then considering a future scenario, 2026, in the year 2026, and we consider about 2.5 gigawatt of storage in the system. So the key idea was to understand the benefits of the storage with different participation models, like what Sassoon explained. There are 2 participation models Ontario has, one right now which is the interim model, and moving to the more enhanced one. So what are the benefits when storage participates with these 2 models? So for that, some of the metrics which we considered in this study, to look into evaluate the economic efficiency, we looked into the energy market production cost, the OR market, operating reserve market cost, then the degradation cost, and then to look into the profits and incentives from the storage owners perspective. We calculated the revenue from the day-ahead market, the real-time market, and what are the profits, both at the individual storage level and at the aggregated level, system level. And then also we looked into the impact on the resource mix when storage comes in the market, how that impacts the resource mix. So we tried to answer some of the question, like with this metrics, we try to understand like how based on different participation model, be it interim model or the enduring model, when storage comes in, what happens, and even if they do it with different storage duration hours. We did it for 2-hour batteries, 4-hour batteries, and 8-hour batteries. And so which option leads to lower production cost, etc. And which option may be more advantageous from the owner's perspective, the battery owner's perspective. Next slide, please. So here we have shown the time series for the locational marginal price, the state of charge, and the normalized power. So this is results for 1 month, January 2026, and we compare across the two cases, like when we use the degradation aware of a curve and the degradation unaware of a curve. So what we can see is like when the degradation aware of a curves are used, it has resulted in, if we look into the power dispatch, because it brings in additional cost, so that has resulted in reducing the dispatch of the battery. That can be seen from the lower figure. And at the same time, when we look into the state of charge, what has happened to it, we are seeing that it has the cycling has reduced. If you look at the middle figure where the state of charge, so the number of cycles is reduced when we account for degradation. Also, the cycles are shallower, so it's shallow cycles. So that is the difference we see when we account for degradation. Next slide, please. So in this slide, we put together the annual production cost, that is the energy cost, the cost in the energy market, and the operation reserve market. So we are comparing across different cases. So the first row corresponds to the base case, and then we have cases corresponding to the two participation models. The row 2 and 3, they correspond to the case when the degradation is not accounted, and the last two rows, they consider the case when we account for degradation. So what we note here is, if you go to the last three columns, the delta operating cost. So the third last column from the right side. So delta operating cost 1, it is actually the difference between the operating cost when we consider storage with respect to the base case. So delta operating cost 1 shows that with storage participation, irrespective of the participation model, be it interim model or enduring model, this is resulting in a reduction in the cost, system cost. So that is what we see. Then in delta operating cost 2, when we compare across the participation model, when we compare the enduring model, that is the enhanced storage participation model, with the interim model, we see that the savings are higher. So it results in a saving of about 2.2 million, 0.16% when comparing it with respect to the enhanced model to the interim model. When the degradation cost is accounted, we see that the savings become lower in delta cost 2. This is because when degradation cost is considered, basically it results in reduced dispatch, like we had seen, right? Additional cost coming in. So that results in a reduced cost or reduced saving, what we see. So it goes down to 1.8 million. Now, when we compare across these two, when we compare the cases with considering degradation without to the case without considering degradation, we are seeing there's an increase, a very negligible increase in the total system cost. This is because the additional degradation cost has been added. So that results. But to note the point that this depends on the market prices too. So the scenario which we so I'm coming to one of the other results where I'll speak more about it. So this is what we see with respect to the system annual production cost. Next slide, please. Now, when we talk about the revenues, what we are seeing is, in summary, the enduring model is resulting in a better performance. When battery participates to the enduring model, the enhanced model, it results in a better profit for it. The reason being it has more revenue in the day-ahead market, lesser real-time market buyback, and which results in a higher revenue. This basically happens because of the reason, because the enduring model has state of charge constraints model within it. So it has a better state of charge management, which results in a higher dispatch for the storage. So that's why it has more revenue from the market. And then when we compare across the case when we have degradation and compared to without degradation case, we are seeing the profit for the storage owner has increased further. So accounting degradation is actually helping the storage owners. So this would we are seeing like this is varying somewhere between 4% to 12%, depending upon which participation model is used and what duration of battery is used. Next slide, please. So this is another interesting analysis which we did. So with respect to the price comparison, so we compared 3 price scenarios. So the first scenario is when the peak prices, the prices somewhat very so the arbitrage opportunity is less, right? The scenario 2 is when there are moderate amount of peak prices, and the third one is the peak prices in the market are higher, the values are higher. So what we note is in scenario 1, irrespective of the participation model or the state of charge band, we are seeing whether you account degradation or don't account degradation, if there are not much price spikes, then it doesn't matter. So the profit we see for the case, this is for the enduring case, by the way. So comparing across, considering degradation, without degradation, there's no much difference. But the case, what results we presented previously, we were seeing moderately high prices in the market. So we are seeing that for lower band, the impact, there's no impact if accounting degradation, but as we go higher, the state of charge level increases. So basically the idea is if battery has more energy to discharge, it can make more profit out in the market, right? So that's why we are seeing at higher state of charge, scenario 2, we are seeing the delta net profit increases for the storage resource. So, and then moving on to the third scenario, what we are seeing when there are price spikes are much more higher, we are seeing in all situations, accounting degradation is helping the storage resource owner, where the profit is going from 11% to about 39%. So if there are more price spikes in the market, so which means more arbitrage opportunity for the storage resource, in that case, accounting degradation when compared to the case when we are not accounting it, this is what we can see. This is some interesting analysis. Next slide, please. So now moving to the closure, I'd like to present some key takeaways from our study. Next slide, please. So what we observed is with storage participation, it has resulted in a cost saving. This is what we are seeing. Adding storage of about 2,500 megawatt has resulted in a saving of about 1.5 to 2.9% reduction in the case when compared to the base case. And this is across various cases analyzed, that is comparing the interim enduring model for different storage battery durations, 2, 4, and 8-hour batteries. Now, comparing the benefits of participation model, we find that the enduring model performs much better than the interim model. And the saving in the enduring model is about from 1 million for a 2-hour battery duration to 3.6 million for 8-hour duration battery. This is primarily because of the state of charge constraint model for the storage, which results in higher dispatch for these resources, which can be utilized during the critical peak periods. Understanding the impact of degradation, what we see is the impact on the total cost. It has resulted in very negligible increase in accounting degradation has caused very negligible increase in the total production cost. However, when we look into the profits for the owners, we are seeing that accounting degradation has resulted in increase of profit for about from 4% to 12%. And also, when we look into the sensitivity of the batteries, we find that the higher duration batteries perform better. It's because of like they have more energy to dispatch. Next slide, please. I think last one. So to conclude and some future paths, what I would say from our study, what do we understand? So there is still more scope for market design and participation model monitoring and evaluation for the storage resource. There's for more innovations what has to come to it. And our observation through this study is actually participation models, the more they evolve, they are helping the system. From the system perspective, what we are seeing is it's very important to understand the complex behavior of the storage resources, which their behavior and in the market participation and impacts, which requires further studies. And from the storage owner's perspective, it's very important and crucial to understand their bidding behavior, right? So, but though we see in our study that including degradation cost is actually helping the storage owners. So that's all some of our important findings. Thank you very much for your patient listening.
Great, thank you. Let's give a round of applause to our speaker. We have some time for a question in the room.
Yujie from MISO. Okay. So when you model the 25,000 megawatt penetration, did you distribute that capacity into multiple batteries?
Yes.
How did you disperse in the system?
So 2500 megawatt, actually IESO did 2 rounds of procurement. So of this 2500 megawatt, about 1500 megawatt, we know the actual location and sizes. We use them, and the remaining 1000, we use a realistic assumption based on their planning, etc. So they were considered 33 units spread across 10 zones in IESO.
Was the assumption that these batteries will not change the LMPs? Or have you observed any crowding effect when all these batteries try to come up with bids and offers targeting similar time frame to charge and discharge. They may just push the price valleys and peaks around instead of, shave the peak and fill the valley.
So what we noted is because with the amount what we consider, right, and on location, it has helped the system to replace some of the expensive generators, right, and bring down the prices. And though we didn't note much of shifting or making the prices flat, one reason being in the ISO system, the prices are widely being set by the hydro resources. So that is what one observation was.
Yeah. Thank you.
Great, thank you. And we have a question from online.
We have a question from Jacques. I am giving you the ability to speak right now. Sweet.
Hi, can you hear me?
Yep, we can hear you.
Hi, thanks. Yeah, my name is Rajat Pungalia. Thanks for the presentation, guys. I have a couple questions, and sorry if I missed it and you already said it. How are you estimating the actual degradation costs in terms of a dollar value?
So what we do is it's a two-step process. One is we model this in the offer generation tool, the degradation cost, what you saw, the piecewise linear. So that's considered in the optimization problem, right? So we this degradation cost component is considered with the optimization. Based on that, the offer generation module produces the output, the offers, and that offers is what we use in the production cost model for as the offers of the storage resource. And once we have the results, what we do is that is actually the raw production cost, and we remove the cost related to these offers because we don't want to double account it. So we remove this offer cost, and then we add the degradation cost, which is calculated offline after the study. So we use the rainflow algorithm. So once the dispatches are available, we use those dispatches to identify the depths, and using those depths we'll calculate the degradation cost. So that is the degradation cost what we reported here actually. So in this method we calculate it offline. So once we know like how it is, we know the discharge pattern. So from which state of charge to which state of charge it's going.
Got it. Okay.
We have one more question.
And yeah, so as a final question from Brian Park. Brian, you've just been given speaking access.
Sure. Hi, this is Brian from FERC. I have a basic question that when you're comparing these various metrics between bidding strategy with and without accounting for degradation costs, I'm just wondering, I assume there's a lifespan difference when you're accounting for degradation and not accounting for it. So I'm just wondering whether you accounted for the difference in the lifespan in those two cases, and is that incorporated into your various metrics that you presented?
So actually, including degradation, what it results in is, if you see, it is resulting in a shallower cycle, lower dispatch from the resource, right? So which is helping to extend the life of the battery, right? So there are studies, research papers which show like if you account for degradation, it increases the life of the battery from 20% to 50%. So that is the after benefits of using degradation. So that itself is not accounted here. Does that answer your question? So basically, so when you use degradation cost, it typically helps to increase reduces the number of cycles the battery would be cycled, right?
Okay, yeah, that helps. So I guess it means that actually the benefits or the it's somehow you're underreporting. Is that right then? Because you said right. What I mean is that because when you account for the degradation, it lengthens the battery. So which means that but if your result didn't capture that, you're actually under capturing the benefit of your bidding strategy accounting for degradation costs. Is my understanding correct?
No, actually, so when degradation is considered, right? So we don't need to separate that out in both cases. So because that itself will prolong the life of the battery, because that will reduce its cycling. That is what we are seeing too, right? So when you use degradation accounted offers, it reduces the cycles, it reduces the dispatch of the battery, and it will have more life. But that is not done for the other.
Okay. Okay. All right. Thank you.
Okay, thank you. Let's give one more round of applause.
Thank you.
Right, and our next speaker is online. Could we have you turn on your camera, Matthew, and make sure that you can be heard in the room?
Can you hear me?
Yes, we can hear you.
Excellent.
Perfect. So our next presentation is from Matthew Cornatian. His presentation is entitled Energy Storage Participation Algorithm Competition, ESPA Comp Design and Pilot Results. Take it away.
All right, thank you. Yeah, so my name is Matt Carnaccio, and I'm from Pacific Northwest National Laboratories. I'm going to talk to you about a market simulation that we did as a battery storage bidding competition. So kind of how we designed it and what we got from our pilot competition. Next slide, please. So we had a pretty big team contribute to this. So we had a lot of people from PNNL help in various capacities, some external advisors. And then I also wanted to emphasize or thank the 4 external participants from 3 different universities who put the time in to actually participate in our competition and make some offers. Next slide, please. So why did we go about creating this whole competition, this energy storage participation algorithm competition? So there's a few things that we're trying to get at here. So one of the main focuses of this competition is to look at electricity wholesale market design sort of alternatives. And we chose to emphasize energy storage. And so there's a lot of questions you can answer here. These are a few, like what role are battery storage systems going to play when they're a major part of grid resources? How do alternative market structures affect the market? How do they affect the battery profitability? And then also what different strategies are battery operators going to employ to offer into the market, right? It's not crystal clear. There's not fuel cost. There's a lot of different ways to choose how to make offers. So that kind of last point is why we chose the competition format, right? It's not a trivial thing to simulate true market participation. Production cost models you can do well, but there's kind of a perfect competition idea built into it. You can make your own agent-based offers, but there's a risk of introducing some bias that's hard to quantify. So the idea is that a competition format where external participants bid into a market that we were simulating gives us the best chance to realistically simulate real-world battery offers. Next slide, please. So ESPA-Comp, we have kind of 3 main features I wanted to highlight. So the first is that we have market structure flexibility. All right, one of the goals is to be able to explore different market structures. So you can easily specify in our Python interface the different market types you want to assess, the number of physical forward and advisory periods, and you can change the time horizons. It don't even have to be uniform. So like the top right corner shows the typical 2 settlement market. So for example, in the 2 settlement day ahead market, there's 36 60-minute interval durations, so 36 hours. And the interval types, the first 24 forward are financially binding, the rest are advisory. And you can set up the real time as well. But you can also set up, something, we did one more dramatic one called the rolling horizon forward, where there's a lot of different intervals clearing at every different times. So for example, the first one, we have 24, the first 2 hours clear at 5 minutes, the next 10 clear at 15-minute intervals, and the last 24 clear at 60. And we chose to make all of those financially binding. So there's a lot of flexibility here. So that's one of the key features here. So we built this in GAMS, and you can put in any market interface, and it will return your answer over as many days as you want to simulate. Next slide. So the second feature, we wanted to focus on battery storage. So we put in a physics-based battery dispatch and a battery degradation model into our platform. And so we chose to use kind of a lithium-ion type generic battery model drawn from a group at Sandia Labs. And we stuck to kind of their zeroth order model on that top right. That's just an open circuit voltage in a resistor. And then we also include a temperature model. So as that current passes over that resistor, it heats up. It's coupled with the environment to cool down. So we can track the dispatch, the state of charge, and temperature over time. We set these up to be a 4-hour battery for their discharging at max capacity. For the degradation model, we have kind of 4 main points that we're accounting for there as well. There's just clock time degradation for how long the battery is around. There's thermal stress for how hot it is, state of charge affects it, and then depth of discharge. And so all those components are converted to a cost to quantify the cost impact. Next slide, please. Then the third, right, since this is the competition, we had to put a whole platform around to allow external users to submit offer algorithms of their choice. Right, this comes from some experimental economics ideas where, these simulations are believed to have the best chance of recreating true market behavior. Not that they're easy to do though. So we built an external platform for this. So we have a website that participants can use to submit their algorithms. We have a virtual machine where we host the system. It calculates the demand and renewable forecasts, price forecasts. It computes what the device is at, the state of charge and temperature. And at every interval, it sends that information to the user algorithm, which is stored on our high performance cluster. They can use that information however they want to create an offer to submit back to the market. We also have a couple other features. We allow state of charge bidding for the users, and we allow users to submit virtual offers. Next slide. Okay, I won't go into this entire workflow, but I kind of want to emphasize there's 2 main modes that we created here. So the first is the sandbox mode, where the users have a chance to test and develop their algorithms in our platform. And so the way this works, the user will go to our website, initiate a run, and 2 things happen at once. Their code is cloned from a GitHub repository onto our high performance cluster. Then at the same time, our VM initiates a market run with conditions specified by the user. The market will then collect data for each interval, pass it across to the other computer for the participant algorithm to use. The participant will create a formatted offer, will go back to the market. It'll iterate until the end of the time horizon and then return results to the website for the participants to see how their unit performed. So after that testing, we have a competition mode where all the users have a time window where they can submit their algorithms. And so once all the algorithms are submitted, then we at PNNL can kick off a market run and start a simulation with kind of predefined specifications. The same process happens, except that now all of the user algorithms simultaneously receive the market input. All of them simultaneously create offers to put back into the market. And then at the end, there's some extra results that are available for the admin as well as the users. Next slide. For our electric topology, we tried to create a reasonably realistic one. So we did the Western interconnection with a simplified topology. So we have 40 buses representing the balancing authorities with 118 transmission lines between them. We aggregated generation by type at each bus and scaled to a 10 gigawatt overall capacity. We put in 12 storage units, each at 125 megawatts max charge and discharge. And then for the other resources, the demand, the hydroelectric, and our renewables, we drew historic profiles by location for each of these sites based on information we had, or the EIA and BPA and CAISO had some information as well. So we got as realistic profiles as we were able to get. We did scale up to kind of a future scenario that's looking at a high renewables case. So you'll note that battery storage, we actually scaled up to be 15% of the total capacity. So it's a major component of this system. Renewables, wind and solar together are 40. and then natural gas and hydroelectric make up most of the rest. Next slide. All right, for the pilot competition, we had 4 participants, and we gave them a 2-month sandbox window to develop their algorithms. Since we had 12 storage units, we divided them evenly between the 4 participants, so each team was able to control 3 of those units. That made all of the units controlled by some user's algorithm. We chose to simulate 3 days in the summer in August, because we've got some energy shortages in that period, so it's kind of an interesting time to check. And then we chose to look at 2 different market structures. So the 2 settlement kind of are conventional with a day ahead in real time, and then a multi-settlement with the same day ahead market, but now in the real time market, we had 23 forward settlements. So we have a full 2 hours of financially binding settlements at every real time interval. We compared these also to a baseline case where the storage units were bid in with a $0 charge and discharge, just to give us a benchmark. And then we kind of went into this with a couple of hypotheses of what we might see. First, we thought, okay, adding additional settlements to the multi-settlement probably could make the battery storage units more profitable. There's more chance to adapt offer strategies based on updated renewables forecasts, for example. And then we also hypothesized that the multi-settlement market would have a higher overall surplus. For similar reason, there's more chances to kind of reach a market equilibrium. Next slide. All right, so we had a lot of results from this pilot, so I picked a few interesting ones I'd like to kind of highlight, and we'll go through for the rest of the talk here. Next slide. So looking at the LMPs, the top is the baseline for both the 2 settlement and multi-settlement. Since the bid strategy didn't change, the LMPs are identical. And these are kind of, like I said, shortage cases where there are some price spikes in the evenings. So then comparing that baseline to the competition below, there are some noticeable differences. The overall, kind of base LMPs don't change too much, but in the 2 settlement and the multi-settlement both, we kind of see a little bit of a shift in timing of those peaks. So the 2 settlement has a pretty similar overall peak, it's just a little bit later. The multi-settlement has a pretty dramatic difference in LMP overall. The kind of average LMP dropped significantly. So a lot less price spikes there. Next slide, please. So what the participants were most interested in was their profitability. This was their score on who won and lost our competition. And so I've got scores posted here for the 2 settlement market on the left and the multi-settlement on the right. And you can look through, there's a couple things I wanted to emphasize though. The 2 settlement profits actually exceeded the multi-settlement profits significantly, and we'll look at a breakdown in a little bit, which was not what we expected with our initial hypothesis. There is definitely room for this to change though, as participant offers evolve. Another thing to notice is a lot of the algorithms tended to group the same. So like the 2 settlement, for example, the JHU team and Li Ping team and Prof. Liu team and Brent team had kind of very similar performance. So their algorithm tended to perform the same no matter which unit it was assigned to. Next slide. So I'm looking at a summary of offers here. We've got for each 4 team aggregated across their 3 units. We have their charge offers in green and the discharge offers in yellow. Discharge is typically higher offer, which makes sense. And everybody chose a little bit different. So the top left team chose a constant offer strategy, which interestingly enough outperformed all the others, kind of suggesting that the market does a pretty good job on its own of assigning profitability. But everybody else picked, a different way of choosing how to bid their prices over the course of the day, but with a pretty similar magnitude. Next slide. In the real-time market, all the participants chose to bid in state of charge, but kind of a lot of variation here in how participants chose to do that. So top left, we see sort of modest positive values. We saw modest negative values from the team on the top right. We have a constant 0 and a high positive case. And we saw, again, the team in the top left performed the best, but the constant 0 case also performed well. I'm kind of suggesting still letting the market decide was an effective strategy. Next slide. Okay, so now I'm looking at aggregating all 12 of these storage units just to kind of see how storage units fared overall in these different cases. So the table on the top left, we compare the two settlement and multi-settlement markets in different figures. So the day-ahead market, first column, they both had pretty similar performance. The real-time markets where the big difference was, which makes sense because that was the difference in the market structure. But this was where we hadn't expected to see the two settlement was much more profitable than the multi-settlement. In fact, units on average lost money in the multi-settlement. We also tracked the degradation cost, like I said. In both cases, again, the degradation cost didn't vary too much between the two. But since the multi-settlement was less profitable, these units in balance tended to lose money considering degradation. Whereas in the two settlement, units came out a little bit ahead. Below on that table, we can also break down the units by cost product. We did include some reserve products here. In this first pilot simulation, we did see that energy took up the majority of the profitability with a little bit in non-spinning reserves. We ended up having zero and in some cases negative market clearing prices in the other reserve products. So units weren't able to profit much, but we didn't have enough time for participants to really explore reserve bidding strategies. And we have room to alter some of the other system reserve bidding choices. Next slide. So now to kind of look at it instead of from the storage unit perspective, from the market perspective, we looked at the overall market surplus, and now we're comparing our baseline case with storage units bid in at 0 to the competition where the users bid in their units. And regardless of the market type, we saw about a 0.5% decrease in overall surplus. That's still fairly significant considering that there's a base demand included in this. But it didn't really matter too much. So we saw that overall we'd say that our competition market was a little bit less efficient, which is part of the point of the competition is we're not always going to have perfect efficiencies. We didn't really see any significant difference, though, between two settlement and multi-settlement. They're roughly the same. Then below the table at the bottom, we can also look at load curtailment and transmission violation. And here in the load curtailment, the baseline case actually had slightly more load curtailed than the competition. So arguably a good thing in that the competition was able to serve more demand. But a little bit higher transmission violation in the competition. All right, next slide.
We lost audio for you. Oh, could you repeat the beginning of that slide, please?
Yes, can you hear me now?
Yep, loud and clear.
Okay, good. Okay. So just saying, we solicited feedback from our participants just to kind of get a gauge on how they felt. And overall, participants had a good experience with this, which was encouraging. There's certainly room for some improvement. Next slide. But a good starting point. And so here we kind of also had some of the comments that they submitted. So there's a range, some negative, some neutral, some positive. A couple of the key negative comments were there wasn't really enough training data to implement a true machine learning algorithm, which a lot of teams would have liked to do. And there wasn't a lot, it was hard to get feedback to really gauge how well an algorithm was performing. So teams didn't have a chance to really optimize their algorithm the way they would like. On the positive side, people were enjoyed the fact that they had an opportunity to test out offer algorithms, and there was a good level of realism to make it an engaging study. Next slide. So overall, lessons learned, the first thing I think we thought was the most important takeaway was that the human learning time was important, not just having machine learning time. But the 2-month sandbox really wasn't enough time for teams to refine their algorithms. So I think we'd get a much better representation of what we're after, of a true market with a longer time window for participants. As far as the market goes, right, I mentioned this earlier, the multi-settlement had the lowest LMPs in the competition. So about $28 compared to, 70 or a little bit more for the 2 settlement. The market surplus values were about 0.5% below baseline in the competition. But again, as offer strategies evolve, that could certainly change by a lot. And then I mentioned earlier, profits tended to cluster by algorithm. So we were able to kind of differentiate between algorithm performance, which was nice to know in this platform. As far as where we're hoping to go next, we'd love to do a competition 1, where we really improve the platform, make it easier to use, iron out a few bugs, and then maybe add some extra features going forward. And we're hoping that this tool will make it available. So academic studies could check different offer strategies, and maybe even industry might be interested in benchmarking their technology. So that's it. Thank you. I'll take questions.
All right, let's give him a round of applause. Do we have any questions in the room?
Yu Jie from MISO New England. I have 2 questions. First, in the day-ahead market simulation, you actually clear for 36 hours, but the first 24 will be used for settlement. Do you think this may impact the profit we've seen in those batteries? And my second question is the multi-settlement and 2 settlement test, the bids from all the batteries are the same? If they are, why would see the small difference in the day-ahead total profit for the batteries? Because I would assume the day-ahead setup will be same for the 2. Thank you.
Sure. Good question. So the day-ahead market horizon, we add the extra 12 intervals at the end just to avoid any kind of end effects of, things trying to force to end at a certain point on midnight, just to help have a more seamless transition. So, depending on exactly how many intervals we put out, it could change the results a little bit. But the idea is that it shouldn't have a big impact on overall profitability. We kind of tried to pick it that way. As far as why the multi-settlement 2 settlement were a little bit different the day ahead, the offer participants had pretty much the same offer algorithms, but those algorithms weren't necessarily static, so they could make slightly different choices based on how their units were dispatched, and there wasn't exactly the same information coming in every time. So if we forced the information to be exactly the same, and the participant algorithms all force their offers to be exactly the same, it'd be possible to get them identical. But over time, we would expect them to kind of converge.
Great. Do we have any other questions in the room? Right, we can turn to our online.
Also, we have one question from Nikun. Feel free to unmute yourself now if you'd like to ask the question yourself.
Thank you. Yeah. Hi, Matt. This is Nicolas, first-year PhD student at Columbia University. I have 2 questions. First is about the energy storage capacity and the locations. Where exactly are 12 energy storage located? Because you are considering the network topology. And also, since the total capacity is only about 1.5 gigawatts, whereas CAISO alone already have more than 9 gigawatts now. Does this competition has insights in revenue loss with increased storage capacity? And my second question is about competition participation. How do participants make sure their bidding algorithm compatible with different case settings, especially consider the physical degradation models? Thank you.
Sure. So as far as the batteries go, we put them into, I think they ended up being distributed at 6 nodes. They're predominantly in the south near a lot of the solar sites, and kind of based on where some of the batteries are today. It's not necessarily where they would be in the future. And so, yeah, so they're kind of spread across California, Nevada, and New Mexico. And then the sizing, we kind of just decreased the overall size of our system to 10 gigawatts. So it's not, that size is not representative of the true Western megawatt scale. But so that 1.5 gigawatts of battery storage was then 15% of our reduced size. But potentially the hope is that it would scale roughly as you see it, but that would certainly be something that would be worth doing, although it would take a lot of time to do the more complex system. And then as far as the participant algorithm feedback, like I said, there's probably room for improvement. They get a return of their profits for their algorithms. So they can always see how well it did. That profit includes the degradation cost that we put in. So they kind of know how that's penalized. But degradation is calculated outside of the market. They know, the participants know what things affect their unit, right? The temperature, depth of discharge, all that. But it's a little bit hard to, fine tune how a particular offer strategy is going to affect your degradation cost, for sure.
Thank you. Thank you.
Great. And we have one more question in the room.
This is Brent. I'm the PI on the project. Another aspect that we learned as we were going through the competition is we first ran it we tried to do just like a one-shot 25 days, I think. We found that a lot of people didn't get all of the formatting and everything right away. So then we reran a specific 3 days of the competition and saw some improvement in just the way that people are taking in data with their algorithm. If we did this again, we would probably run it differently, doing smaller chunks of time and letting people update their algorithm, figuring out, which aspects of degradation are really important for us to include in those sorts of questions.
Great, let's give one more round of applause to our speaker.
Thank you.
Okay. Our next speaker is Alexander Rutkevich. He will be speaking on evaluating benefits of long-duration energy storage.
Thank you. Thank you, FERC. Thank you, everybody. Hopefully my presentation, which I uploaded this morning, made it. So this presentation is about evaluating the benefits of long-duration energy storage. A bunch of participants of this work are my colleagues at TCR and also my partner Russ Philbrick with Polaris Systems Optimization. Next slide, please. So the first point, we have a brief discussion of what does it mean to look at the long duration storage as it sort of affects the multiple time scales. And as an illustrative example, we will look at the use of the Hydro-Quebec hydro system as a long duration storage example, and kind of look at sort of what the valuation methodology may look like, talk about basic storage economics, modeling framework that we used, and analysis at different timescales, and some market design implications of what we observed. So next slide, please. So first of all, if we'll look at the long duration storage, then there are definitely very different timescales at which the benefits may accrue. So the long term and the benefits may translate into different composition of the generation mix, whether you have the storage or you don't. The midterm, that may go from weeks to months. These are maybe kind of different seasonality of the use of the storage. And that is generally not addressed by, day ahead and intraday market structures. So then the day ahead is like a daily, that's a typical daily arbitrage and use of storage for reserves. And then there's also the intraday, intra-hour real-time framework. So all of these time scales produce different categories of benefits. So the one of the challenges is sort of integrating it all into one analytical frameworks if someone wants to evaluate sort of the investment in storage and the benefits of that. Next slide, please. Now, when we look at the benefits, again, we focus typically on two categories. One is what the owner of the storage sees, and so essentially that translates into net revenues that the owner receives, and in that sense, the challenge here is sort of someone has to have a very coherent modeling framework so that the different categories of benefits were consistently accounted for. The societal benefits usually looked at using what is known as adjusted production costs. So when you have two cases, one with storage, another without storage, and you look at the change or in the production cost within a certain time footprint, but at the same time, you also have to focus on what happens at the change of the interchange with the neighboring system, and how to account for that and properly accounted for the loop flows and everything. So there is a certain technique accumulated in the industry on looking at how to evaluate different projects. And in that sense, storage is not an exception, but again, we have to look at a longer time frame. Next slide, please. So the example case is the hydrocubic system as long duration storage. So the idea is floating in the literature. So imagine like there is a dedicated HVDC line going, say, from New England to Hydro-Quebec, and the energy can be sent from New England to HQ system, parked there for as long as it needed, and brought back. And it's could be used as a very flexible system. So the objective is to examine the methodology. It's not a study of any benefits of any specific system. So please don't interpret it that way. But it is based on a very detailed modeling of the power system of New York and New England, and based on the data sets assembled by TCR through their years of evaluating, for example, offshore wind procurement process in New England, which is sort of allowed them to have a very up-to-date model, both of the ISO New England system and New York ISO system. So the again, the physical parameters of this system are quite considerable in size, but I'm not going to disclose them simply to avoid any misinterpretation, because it's an illustrative case. Next slide, please. So the the data set that was used, it includes the load forecast, transmission topology, the generation mix, representation of the capacity requirements in the capacity markets, all the environmental RPS type policies in place, emission caps in Massachusetts. So all of that, plus the assumptions about the future available technologies, their costs, and also projections of fuel and emission data. So all the sources are primarily, all data come from public sources, and similar assumptions for New York ISO system and for ISO New England. Next slide, please. Now, for the evaluation, there was a use of the analytics powered by PSO platform, which essentially involved three categories of models: the capacity expansion model. Then there is the HQ storage rationing model, and I'll talk about that. And then the third one is the standard energy and ancillary services model, which represents primarily the day-ahead market for New York ISO and ISO New England and the interactions between the two. All of these models, what's important, they implemented within the same platform and rely on the same data. So all the information and solutions they are consistently accounted for. Next slide, please. This is just acknowledgement that the analysis was done with the use of analytics platform powered by PSO, which allows to solve different categories of problems within the same framework. Next slide, please. So the capacity expansion model, its primary objective was to identify sort of the impact of the storage on future capacity mix. What would be new retirements and additions. So in that sense, the biggest challenge of modeling storage in the capacity expansion, and that's so there's nothing new here, is how to balance the granularity in time with granularity in space and representation of the assets. So because the optimization problem becomes very big, and either you have to aggregate sort of the assets, and then the solutions would be difficult to interpret at subsequent stages, or you have to sacrifice the temporal resolution of your system and have a stylized representation of time within the years, because the thing is going over probably like 3 decades of optimization. Now, representation of the storage essentially is to kind of the assumption is following: the charge and discharge set equal to the transfer capability of the HVDC line in both directions, same capacity, and the efficiency is essentially related primarily to the round trip losses on the transmission system on the line itself, plus the losses in the HVDC on the hydroquebec side. Storage capacity assumed unlimited, because we don't know what it is. We may use this to size it, and there is a renewable energy constraint. So the assumption is that all the sort of flow on the HVDC line out of New England sort of must be supported by the concurrent production of renewable energy. So that pretty much guarantees that whatever energy goes back and forth could be considered clean energy. Next slide, please. So the solution of that pretty much sort of produced some changes in the capacity mix, both in the size of the like battery storage, how much capacity was added, also affected some retirement conclusions. The HQ, the rationing model. So this is important because essentially what we need to decide is how we're gonna use the stored energy over time. And the horizon here is like something like a year, right? So I can store energy produced in the spring, hold it for the summer, and then in the fall, hold it for the winter. So that kind of things. But the question is how we decide when to put it and what to put. So that the idea sort of the, in order to solve this problem, we configured PSO to run one effectively kind of optimization over 8760 hours, right? Now to accommodate that, we have to relax commitment constraints, because solving unit commitment over that period of time would be a bit challenging. So, but otherwise, the system solves to effectively provide the essentially the schedule of the storage use on an hourly basis. So the idea is that the key output that we want to take out of that is not really the hourly profile, but mostly the end of day state of charge as a target, because that gives us the plan how to use the storage. And we ran it in 2 modalities. One is essentially minimizing the cost, and another modality, given the prices as an input, and I'll explain where the prices are coming from later, maximizing the storage profit. Next slide, please. So the energy and ancillary services, that's a standard security constraint union commitment economic dispatch of two markets with some level of coordination between them. So the model gives us the prices and actually optimizes operation of the storage itself and produces the LMPs. Next slide. Now to explain some things, probably useful to set up a few concepts of the storage economics. So kind of what the key parameters are the gross price, the net price, the holding range, and the marginal value of energy in storage. So essentially the gross price is what it costs to add 1 unit of energy to storage. So essentially you would be accounting for the price you pay plus the round trip efficiency loss and whatever other things may be considered, including the accounting for opportunity cost of reserves. And then the net price is essentially what you get out of selling a unit of energy from your inventory. That may include obviously the LMPs, the opportunity cost of reserves, and also any other storage related costs. So now we've got a range between these two prices. The gross price is bigger than the net price. So that is the holding range. Now, why it's important? Because there is another characteristic, which is marginal value of energy in storage, which is essentially the shadow price for the state of charge constraint. So then effectively the behavior of when you charge and when you discharge depends on how the value of energy corresponds to gross price and the net price. Next slide, please. So essentially, like orange line here is the gross price, and the blue line is the net price. So if your LMP is above the gross price, you would charge your storage. But if your LMP is below, then you would discharge. And if it's in between, you would wait. What? No, so sorry. You're right. If my value of energy in storage is greater than LMP, that I would charge, because it's more valuable to have this energy inside. If the value of energy in storage is less than the net price, then I would discharge, because it's not as valuable as the market price. And if it's in between, then you hold your energy. So that's basically kind of very useful concept, and I'll explain why later. So next slide, please. So when we model the rationing, so essentially you can think how would you in practice use it, right? So you would run it as kind of as a roll and horizon optimization, like I don't know, daily, weekly. You would look a year ahead, say, well, given what I know now, what my state of charge now, what my forecast is, how would I optimize the use of storage for the next year, right? So take this decision, and then next day or next week you would reconsider it given what occurred, right? So that sort of we try to emulate the same process and develop by running a rolling horizon of this optimization, get ourselves the schedule of the storage use in that sort of rationing mode. So the question is, however, who runs this optimization in reality? Would it be system operator? Would it be storage owner? And how this scheduling going to be communicated to the market? Because that's actually a non-trivial question. What is it you're gonna do? Okay, you've got the schedule, then what? And at this point, there is nothing in the market design that says how to use it, right? Next question, next slide, please. So we looked, this is actually the kind of the result of this optimization done for 2 years, like 2 future years, 2035 and 2048. The 2035, why we use these 2 years? 2035 have already significant level of decarbonization in both systems. 2048 is a radical level of decarbonization with a lot of stuff going on. But interestingly enough, if we look sort of on a day-by-day state of charge, the shape is sort of have the same trend. So what we do, we begin with the storage being about 70% full in the beginning of the year. And then that's on January 1st, right? Then we pretty much discharge it because we use this energy. Prices of price of gas are very high in New England, so the LMPs are high. Then in the spring we charge. In the summer we kind of use it, right? Somewhat, but pretty much hold because for the forthcoming winter we need that energy. And we see that pattern pretty much in both years. So next slide. Now, how do we communicate it into the energy and ancillary service model? There are two modes. One, we give the end of day state of charge as a target. And basically, when we run the energy and ancillary service model, to the end at the end of every day, we need to meet the target. Now, the target could be interpreted as a hard target or as a soft target. In a soft target version, we put the penalty set by the shadow price, by the value of energy in storage. Except that we initially tried to use the long-term optimization shadow price. And that produced pretty disastrous results because the long-term optimization produces prices which, given the storage, which connects the marginal resources across the entire year. And these prices are completely inconsistent with the way the prices are formed in the market today, because nobody looks at the possibility that you can trade the resource in January with resource in July, and vice versa. So the shadow prices that we found, those were not very helpful. However, when we took the same end of day charge and re-optimize it on a short-term basis, as in one of the decision cycles in PSO, and produce the short-term shadow prices, those were passed onto the unit commitment algorithm. And those happen to be very helpful. So now we have two cases, the hard target and a soft target. Next slide, please. Now, this is again a non-trivial thing, because even we say that we have a daily target, the way the model does it, it enforces the target at the end of the optimization horizon. And the optimization horizon is not 24 hours, but 72 hours. We have a 2 days look ahead. So essentially, at the end of the horizon, I meet the target, but the model effectively is permitted to re-optimize within the horizon. So at the beginning of the delta of the next day, actually my state of charge could be different. And that's why the setting it as a soft constraint turns out to be helpful. So next slide. So now we've got results, and I just show them kind of in relative form. So the blue bars are hard constraint, and the orange is the soft constraint. So it's the same target. So we can see on the left side, this is the adjusted production cost relative to no storage case. And we see that having a soft target have a significantly better, especially in the first year, production cost saving than the hard targets. But interestingly enough, the same thing applies to the storage profit. The soft target also increases the owner's profit, which is okay, fine. Interesting observation. Then we said, okay, what would happen? So if I take the prices from that the best case I have here, like with a soft target, and say, that's my projection of LMPs. I have my storage in place. It's optimized, right? I should have a pretty decent hourly projection of LMPs. Why don't I use these LMPs and re-optimize the schedule of a storage, right? Then from a perspective of the owner, to maximize owner's profit. Okay, and then see what happens if I use these targets and communicate them to the market. So next slide, please. So now I actually have three options. One, I can just give the market the entire schedule, 8760 values, right? And say, well, you know, see how much money I will make. The second, I'll give it as a hard target. And the third, again, like in the previous case, I'll give it as a soft target. So then the first question, what happens to the overall, after I re-optimize the schedule, what happens to the kind of rationing? So the next slide, please. And here I'm just comparing for 1 year, but both years look about the same. So the blue line was the original rationing schedule, right? And the orange line is the new one, which intend to be profit maximized. Pattern is similar, except that we see we don't see that deep in the summer anymore. Somehow that sort of pricing structure suggests a different dynamics. So let's see what it means in terms of the cost savings and revenues. Next slide, please. So the first two bars are the previous case, which was the cost minimization results. And then the other three bars, the green, the blue, and the purple, these are the profit maximization. Well, first of all, as we see that impact on both on production costs and on profit may be pretty devastating. We think we're maximizing the profit. We give this information to the market, and this is what market does to your profit. So which may turn from profit to loss even in some cases. Especially sort of, I think this green scenario, which is just given the schedule. I self-schedule the storage. I thought I was maximizing this for profit. At the end, I can actually end up losing money. And that was a pretty healthy profit to begin with. So the conclusion here is that actually it turns out that the soft target cost minimization strategy appears, at least in these simulations, both the best from the cost minimizing standpoint, but also from a profit maximum. So letting the RTO to maximize your basically operate your storage and manage your state of charge. If you can communicate well-designed targets, or let it design the targets, that's actually maybe at the end quite profitable to the owner of the storage. I mean, it remains to be confirmed by other sort of studies, but in general, kind of that was a bit of a surprising conclusion. So the bring it to the end, last slide, please. So in general, what we see that the benefits very much depend on the market design. So really has to give it a lot of thought on how we, especially for the long duration storage, how we do it. And the active participation of system operator is crucial, actually, for this type of thing. It's hard to, I mean, given what we see, it's may turn out to be a very risky business to, ration your storage over longer duration time and may lose money. On the sort of that's the developer should be closely participating in the design of the market, because otherwise it may turn out to be a disastrous outcome. And from a analytical standpoint, it's very important to have a comprehensive set of models when you analyze them, because when you just jump from one stylized model to another stylized model, as we see, you would expect that the model tells you, oh, I've got a lot of benefit out of it. You put in a different model, and it's not there, even with the data that are coherent. And I can imagine what happens if they are. So with that, thank you very much.
All right, thank you. Let's give them a round of applause. Do we have any questions in the room? All right.
Russ, you're not supposed to ask questions. You're a coworker.
Yeah, well, I haven't seen these results. So the profit maximizing schedule that you determined, I would assume that for a resource of this size, there would be a significant impact on market power, and that therefore the change in dispatch that you get by taking the prices and re-optimizing the resource would affect the prices. And so therefore that would explain why it was not a great plan because of.
Yeah, I mean, generally, I would say the size and the long duration storage would always affect prices.
Yeah, right.
I mean, it's whether you are profit maximizing or not, having it or not having it, it will be different price.
Okay, so is that the primary story then of why the profit maximizing strategy doesn't do well?
Well, I mean, that's strange. However, right? You would assume like, we optimize, but the price formation changed. Right?
Yeah, exactly.
Price formation changed. So that's why it's so important to understand how the prices are set, and if you want to get something, how you communicate it to the market so that you just don't destroy yourself.
Okay. One more question.
Yujie from MISO New England. So I have a question about the value you put for the end of day SOC. In your simulation, you put the SOC tracking constraint at the end of 72 hour 72. Have you considered, say, using the forecast LMP for the hour 73 as the value for the SOC?
I don't think it's the right value for the SOC to begin with. Why the LMP in the hour 73 would be a right value for the SOC?
Because my thinking is, say I holding certain amount of SOC at the end of the day. I'm comparing my the LMP at hour ending 72 versus 73. If I see 73 price is higher, I will hold the SOC and maybe discharge 1 hour later.
I mean, I may hold the SOC even then, because if I have a longer term view, right, then actually, as remember, we have a range of prices within which we hold, and we don't know where within that range. So the point was that if I have a target at the end of the day, and I know where's my starting point, then and I do optimization, then I get the value of energy and storage as a shadow price.
I think SOC tracking constraint, the shadow price is more reflecting of the opportunity cost. But here we're looking at the kind of like a demand curve for the SOC value at the end of the day. So I'm not exactly clear like whether we can directly use the SOC tracking constraint shadow price.
Okay, I think we need to talk through this, because it's yeah.
Thank you.
All right, thank you. Let's give him one more round of applause.
Thank you.
Okay, thank you. And our final presentation today will be virtual. It is from Nick Zhang. Nick, could you turn on your camera and speak into the...
Yes, can you hear me all right?
Yes, we can hear you just great. So this presentation is entitled A Theoretical Framework for Monitoring and Mitigating Energy Storage Market Power in Real-Time Markets. You can take it away.
You see my screen now? Sorry, let me figure out my slides.
Yep, we can see you and you're good to go.
Sounds good. Okay. So good afternoon, everyone, and thanks for staying with me since it's already 5 p.m. and everyone is hungry for dinner. And I'm Nicolas Zheng. My friend also call me Nick, and I'm a first-year PhD student. Work at Columbia University. Working with Professor Bolen Xu. And today I'd like to share joint work with our visiting scholar Zhiyu Zhou and her advisor Ruifan Zhang from Xianzhou University. And this work is about energy storage market power in real-time market and about how to monitor it and mitigate it using with some theoretical support. And everyone in this room, also in the Zoom, knows how important energy storage is in decarbonization, and also we know the capacity of energy storage increase exponentially. For example, in California ISO, the installed battery capacity
Hi, Nick,
was
could you, if you're sharing your screen, could you enhance the size of your slides? Or
right.
turn off
All right.
screen sharing?
Sorry about that. Maybe I'm
No worries.
using a second screen now. So
Yeah, we're seeing it as a vertical monitor.
right,
Do you think,
let me just
Rob, do you think you could
use
pull
the
up the
second
slides?
second one here.
Nick, and if you're okay with it, Nick, you could stop screen sharing and we could display your slides. But this looks a lot better.
Can you say it all right now? Just wondering.
This looks better. Yeah.
Okay, sounds good. Sorry about that. Yeah. So everyone knows that energy storage is important, and we already have
Nick,
8.6
could you,
gigawatt.
what slide can you repeat what slide you're on for our slide?
This was slide 1, and this is slide 2, and I was talking about this one. And I want to like start from beginning. All right.
Okay, look, it's all good now. Thank you.
Oh, okay, sounds good. Yeah, thanks for. Before, sorry, I didn't test my video before. So everyone know there's a lot of energy storage in CAISO, and the number has go up to over 9 gigawatt right now. And the most important thing here is that most of them are owned by independent power producer, and therefore they are profit seeking, and their market power cannot be ignored. And however, the market power of battery energy storage is very hard to monitor and mitigate compared to gas, where their cost structure is very clear. They use gas and their price based on gas price and also their heat rate. And it's very easy to monitor their market power based on that. Compared to batteries, they have very different price structure. So they have degradation costs and operation variable costs, and also most importantly, opportunity costs. And the opportunity cost is the hardest one to monitor, because it really depends on their private prediction for the future prices. And it's very hard to prove their opportunity cost as proper or not. And therefore, to analyze the behavior of energy storage exercise market power is very important. So this work, we compare the bidding behavior between price maker and the price taker in the storage. So here is the outline of this talk. First, we talk about how we model the energy storage arbitrage problem, and then how we model the price maker and the price taker in the storage differently. And the third, how those energy storage design their optimal bids. And the second part, I will talk about our key findings, the theoretical economic withholding bound, which is a bidding difference between the price taker and the price maker and the storage. And this withholding bound solely depends on price expectations for the future, and therefore it's very easy for ISOs and RTOs to use. And the last part is about a case study. We verify this withholding bound using New York ISO price data, and also show how price taker and the price maker and the storage behave differently in the market. And the first, to model energy storage price arbitrage problem, the easiest way is to model a multiple interval problem here. Let me use a laser point. So this is a multiple interval problem.
Just quickly, just make sure to say next slide to get your slides to advance, since we're screen sharing. Sorry about that. Go ahead.
Oh, okay. So so here the energy storage arbitrage problem is a multi-interval problem. and where
I'm sorry,
they
Nick.
can-
I think that you're still operating on your personal screen, but that's not what's being displayed in the room. In the room, we're sharing the screen from an AV center. Yeah. And
okay.
this is currently being
Okay,
presented.
then maybe you just like I already passed this and the next slide. Sorry about that. I was sharing my slides.
No worries at all.
So maybe next slide. And again, this is about like the difference between gas and batteries and how difficult the battery storage market power is hard to monitor and mitigate. So it's important to analyze this battery storage bidding behavior when they exercise market power. So next slide, please. So this is the structure of the talk, and the next slide, please. So again, here is how we model the energy storage arbitrage problem. So we model it as a single period problem using dynamic programming, where energy storage are trying to maximize their profit. The PT minus BT is a discharge minus charge, multiplies the price. Here should be lambda tilde, and minus the discharge costs. Here we can engineer the degradation costs and other operational costs here. We assume this is like proportional to your discharge power. And the last term here, we use the SOC value function, which is very typical in dynamic programming, subject to several physical constraints. Next slide, please. So the problem is how we model the price maker and the price taker answer differently. So if you are a price maker, you are exercising market power while bidding. So you, based on your predicted price, you know that your operation will have effect, will have an influence on the market price. So you add another term called the price influence function or price influence model. So here we assume a very simple one. The price influence is related to your operation, which is a discharge power minus the charge power. So it should have 0 value at the origin, because if you have no behavior, then the price will be not changed. And also the function H should be decreasing. If you are charging, then you will increase the price. If you are discharging, you will decrease the price. And if you're a price maker, you assume your bid or your behavior will have influence on market price. So you model your price based on your price prediction and your price influences. And if you're a price taker, you are just using your like price prediction. So you are not exercising your market power. So next question is how you design your optimal bid based on these two assumptions. Next slide, please. So here we have the opportunity function for the dynamic programming. We have first term is market revenue, and the second term is operation costs. And actually, when you're bidding into the market, you are leveraging your market revenue with your costs. So the operation cost is what you need to engineer into your bids. And for the value function here, there are some good property with this derivative, which we call a marginal value function. It's non-increasing, and of course, you can calculate backwardly if you know the future price or you know the future price distribution based on some prediction models. So when we design bid, we can use KKT condition and prove it non-trivial to show that the charging bid is actually just a marginal value function and justifies the efficiency eta here. And for the discharging bid, it's also like a value function adjusted by efficiency and the degradation marginal costs, discharge marginal costs. And we can observe that the difference between price maker and price taker bids is simply the difference between marginal value function, and it's adjusted by efficiency. So it's linear to the difference in marginal value functions. And therefore, in the following slides, we are comparing marginal value function between price taker and the price maker, and it's equivalent to compare their bids. Next slide, please. And here we show the main result we find, and the value function difference, or we should say the bidding price difference between price taker and price maker is solely the upper bound of this gap is solely depends on the expected future peak price and expected current price. Or if you know the future price, it's a deterministic case. It solely depends on the future peak price and the future and the current price. And the good property of this one is that it's distribution free. So no matter what the distribution of the future price, real-time prices is, and even you are using different prediction models, it's not related to that. It's just relies on the expectation for the price, not about the distribution or the model. And the second is model free. So no matter what kind of price sensitivity model price maker and storage is using, it's one effect, like a difference between if you are bidding truthfully or you are exercising market power. So next slide, please. So to prove this, we use two cases. First is like we have no price uncertainty, deterministic case, and the second is stochastic case. So we assume there's uncertainty in the real-time price. And the proof is two cases with same steps to prove it. And first, we calculate the marginal value function for price taker and price maker, and then we calculate the maximum difference between them, which we call as upper bound or economic withholding bound. Next slide, please. So here again, we show the objective function for the dynamic programming for price taker and price maker. And we can calculate the marginal value function analytically and backwardly if we assume like a fixed terminal SOC marginal value function. And we can use these two closed form in this blue block here for price taker and price maker and calculate the value function backwardly. And here are 5 different cases for price taker and price maker. Next slide, please. So simply different threshold for the real-time price. From low price to high price, you would like to fully charge or fully discharge, or partially discharge, standby or partially discharge. And we're able to calculate it very fast, like very checkable, no matter you are like there's uncertainty in price or there's no uncertainty in price. Next slide, please. So since we can calculate price maker and price taker marginal value function, then we can calculate the maximum gap between the price taker and the price maker marginal value functions. So we call it as economic withholding bound, or here we represent this with theta. And the theta t, we can also get as a closed form here. And the only term we care about is the second term, because other term we got the value passed from the next period. So if we assume the terminal value marginal value function for price taker and price maker is identical, then the terminal theta here is all 0. So the only external thing, like the new values, are come from the second term. So the theta t, maximum theta t, must be less or equal to the maximum second term. And the second term here, again, so because the marginal value function is non-increasing, so the maximum value we can take is as 0 SOC. And so it's small or equal to the value function of the price maker as 0 SOC minus the real-time price divided by the efficiency. And then it's less than or equal to the future peak price minus the cost. The proof is also trivial and intuitively, because your marginal value function value as 0 SOC is that was the maximum profit you can make, which is the future peak price. And next slide, please. Similarly, we can prove in a very similar manner, except for the if there is a price uncertainty. The only difference is that instead of we have like a deterministic price, we have to calculate the value function backwardly using a price CDF and PDF, and still we can derivative closed form. Next slide, please. And with the price uncertainty, we say that the economic withholding bound is solely depends on the expected future peak price and expected current prices. So it's very easy for ISOs and RTOs to use and provide a very strong theoretical support for market power mitigation based on their bids. And since we have these theoretical results, the next question is how could we verify it under the real market price? So we have our case study with MISO prices. Next slide, please. So here we have the two energy storage. One use their price maker model, one use a price taker model, and both of them have 2-hour battery and 90% efficiency. And we use the real-time price for MISO to do the simulations. And here we see the orange curve here is a price prediction, and the blue lines here are the charge and discharge power for price taker and storage, and the red ones are price maker and storage. And here we see, because there's a bit different bits, so the cleared energy power is different. And we see even there's no power, physical withholding, you can still withhold your power with your different bits. And next slide, please. So here we compare the marginal value function and verify the economic withholding bound. So here we see if you are a price taker, then your marginal value function will much more steep compared to the if you are like price maker. And also on the right hand side here, the blue curve here is the theoretical withholding bound. And we see that the real gap between price taker and price maker gap is really below this withholding bound. And therefore we prove that our theoretical result is valid. And next slide, please. And also we did some sensitivity analysis. If you have different level price influence in the market, ranging from zero influence to like a higher influence, like you have 0.02 influence based on your operation. So we do see that you will be more conservative and withhold more power if you have high influence on the market. And on the right hand side, you may ask one question about like if the energy storage agent have incorrect prediction for the price influences, what will their revenue looks like? So here we compare the actual price sensitivity with the energy storage agent predicted price sensitivity. We see a ridge shape. So if you have accurate price sensitivity estimate, then you of course will have highest profit. And if you have a higher estimation error, forecast error, then you will lose your profit. And also if the price sensitivity is higher, your profit will also going down. Next slide, please. So to wrap up, here we propose an analytical market power examination framework, which provide theoretical support for ISO and the RTOs to regulate energy storage bids. And the most important property of the bid gap between price taker and the price maker and the storage is their maximum difference solely depends on future price expectations. Therefore, it's very easy to use. And you can even use day ahead price for these expectations. And some extension and future work will be about, first, we would like to, here in this work, we assume a time invariant price influence. And in the future work, we'd like to see what if the price influence is depending on the market dynamic, also the previous energy storage operations. And another thing is we would like to test the different energy storage, one is price maker and one is price taker, how they can change the market dynamic in market simulations, and see how energy storage have economic withholding affects the market dynamics. And next slide, please. And thanks for your attention, and stay with me. It's already dinner time, and I'm happy to take any questions. And thanks to my collaborators and my advisor. Thank you. And for more details, I have the reference for my paper. Yeah.
All right, let's give him a round of applause. Do we have any questions in the room? Right, one.
In general, this is Alex Rutkiewicz, Newton Energy Group. In general, when you consider conventional generation, that in effect, the market guarantees that the generator would never run at a loss. Right, so it may, on one hand, its market power is mitigated, but it would never be asked to operate in the course of a day and lose money. There is an uplift that is being paid. So does your market mitigation mechanism still guarantees that the storage would be made whole in the course of a day?
Oh, that's a great question. And the question is about like if we have some kind of mitigation method for energy storage, will still energy storage still earn profits in the market? So first, we are not proposing a specific mitigation method, but like we provide ISOs and RTOs theoretical support. Like how could you like monitor their like their market power? And about the like revenues in the market, I think there is a lot of like outside of market left beyond the like basically energy market clearing, especially when you consider capacity market. Energy storage are cleared in the awarded in capacity market, but sometimes they are not able to be there because of the low stable charge, and therefore. So sometimes you have to consider energy storage under some price mitigation. You have to force them to offer. Like in CAISO, you have like a exceptional dispatch. So they force them to must charge or discharge. So this is also another kind of like force energy storage to do something, right? So it's very hard to guarantee. Like if you have specific kind of mitigation method, you can still guarantee their profit. But like to my knowledge, if we keep investment in energy storage, everyone will lose money in current market setting, even there's no mitigation. Yeah.
Well, that's a different thing. When you do not cover capital cost is one thing, but if you are made to operate at a loss, because your system says, well, you gotta run, but you're not guaranteed to recover the money. That's actually very bad business.
Yeah, actually, when you bid truthfully into a market, you can still earn substantial profit. If you are on a price taker setting, if there's not so many energy storage market. So some of our group side work already proved it. So even you are training your bidding algorithm using a price taker assumption in the market, you can still earn substantial profit. But here we are talking about like if you are trying to withhold your market, withhold your energy storage and bid like as a price influence or price maker, then how you will like bid differently. So you are not bidding truthfully. So therefore we need to mitigate your market power.
Okay, let's give one more round of applause. All right, this concludes the session for today. Thank you guys for coming. Thanks to our online participants. We hope to see you guys tomorrow if you're registered, and thanks for bearing with us through our mishaps, and have a great rest of your night.